we should start or not. An important thing is that we will have a live transmission in the YouTube channel, which the address has been sent to you. And eventually, some questions will appear here. So maybe the chairman section could keep watching whether someone who is watching on the YouTube channel has some comment or question. And when you make question to the speaker, you please use the microphone, because then the YouTube people will be able to listen to you. Okay? The other thing is that we have this 3-qubit quantum computer here. So, it tells you the total time of your speak, and here it tells you when you have only 10 minutes to finish, and then it's a countdown. When it reach these 10 minutes here, the yellow light will flash. When it ends this time here, it explodes. So you have, okay? So the speaker has just to start there. Oops. This is local technology. And it's just a countdown, okay? And when you finish, we just reset. All right? So Thaisa, we have to change that because Alexandre has 1 hour now, but I'm not sure. Okay, I will show you how to do that. So I guess we'll have Alexandre tutorial now, and then after that, the breakfast. I like this kind of conference. The coffee break comes, not the breakfast. The coffee break comes right after the first talk. Okay, I don't know, Thaisa, do we have any further question, Thiago? Tomorrow also the poster section will be at the same place of the coffee breaks. So tomorrow there will be these stands to hang your poster. So who is going to present the poster can hang the poster as you come. There is no, you just choose the place and hang it there, all right? And the afternoon poster section has a little surprise for you, thanks to Thiago. We'll be a little bit more alcoholic. So that's to stimulate the cooperation among the groups. So alcohol used to help a lot on that. So okay, so anyone wants to make any question? If not, I think. What do you think? What do you think, Thaisa? We should start. We'll start 10 minutes early. Alexandre is okay with that? Okay. Thank you very much. She'll send a message. Okay. Anyway, we should have place for 40 posters, so the space should not be a problem. Yeah. I should say that who comes first and just hug the person. That's the easiest thing. Ok? Ok, Alexandre. Tá funcionando isso?
Okay. It's working? Okay. So thank you very much for the invitation. Thank you for Thaisa who invited me. Okay. So my name is Alexandre. I work here in CBPF as a researcher. So my field of research is doing quantum experiments on quantum information. Okay, I mainly work with NMR. So today I will give a short tutorial about how you build some quantum thermodynamics experiments with NMR. Okay. Sure. Okay. So maybe now I have to wait 1 minute. Okay. So first of all, I will give you some short introduction about what is NMR, how it works. Okay, for those who doesn't know what is NMR. So in NMR, okay, we work with I have some problem here. Maybe can I change it to PDF? Change trocar pelo PDF. Não está aparecendo. Okay. Now the illustration appearing here. So in MR, we work with a symbol of molecules, okay? The qubits are nuclear spins you put in the magnetic field, okay? So if you have 1/2 spin, you have 2 levels, and each level is a level of a quantum bit, okay? So we have many of molecules. Usually work in liquid states, okay? The simple molecule you have to implement experiments is the chloroform. Okay, it's the chloroform molecule. Okay, you have here 2 qubits. Okay, the nuclear spin of the carbon and the nuclear spin of hydrogen. Each one is a qubit. Okay, and they are coupled each other, so they form a 4-level system that you can label as 0, 0, 1, 0, 0, 1, and 1, 1. Okay, so it's the simple system. The simplest system that you can perform experiments on NMR quantum information. Okay, so this is basically the main setup for the experiment. Okay, you have a sample with many of molecules. Okay, a sample of molecules you put inside a magnet. Okay, here is a picture of magnet you have here. Okay, and so you put the sample inside the magnet, okay? And then you have the splitting of the you have the Zeeman splitting, okay? So then you have the qubits there. So around the sample, you put some coils, okay? Which is your probe, okay? It is a picture of a typical sample, okay? It's a liquid that you put made of molecules, okay? This is the main scheme of the experiment. So we have a transmitter that you create the RF pulses, send them to the probe. The probe is mainly the probe is a resonant circuit, okay? So you tune the circuit to the Lama frequency of the spins, okay, and send pulse to this probe, to the sequence, okay? The sample goes inside the induction element here, okay? So when send pulse for this sequence, this coil here, okay, creates some magnetic fields that you use to manipulate your sample, okay? And the signal is also measured here, okay? So if you have after you put your sample in a magnetic field, okay, and apply a ref pulse and take your sample out of the equilibrium, okay? So because your spins are inside the magnetic field, they start to process around the magnetic fields, and then you capture the signal of the spin processing in the coil, okay, in this coil here. So we have a typical NMR signal, okay, like this. So here I show a typical coil that you use on NMR is in this format here. So the coil creates a magnetic field like this, okay? So for example, create this coil here. The sample goes inside here, okay? and this coin create a magnetic field at this direction. Okay, for example. So what you do is usually to apply some RF pulses, okay, which looks like this, more or less. So you have a signal, okay, with a frequency equal to the frequency of the Larmor spin of the qubits, okay, and you modulate this signal here by whatever you want, okay, and a typical modulation is just a square pulse like this. So you send this square pulse to the sample, okay. So what happens if you send this square pulse to the sample? What you have this coin here? You create a magnetic field, okay, in some direction. Let's say that this direction here, okay. This direction here is x direction. So you create a magnetic field, oscillating magnetic field in this direction x here, okay. If you look in the laboratory frame, okay, but the spins are processing, okay. So if you look the movement of the spins in the rotating frame that process together with the spin, okay, so you're gonna see the magnetic fields like this, okay. You're gonna see stacked magnetic fields. So in the rotating frame, okay, the magnetic field created by this coin here will be static like this, okay. So because the spin couples to a magnetic field with this Hamiltonian here, okay, you have this evolution here, okay. So what happens is that this pulse here, okay, this pulse here in the rotating frame implement rotations, okay, because this is a propagator of rotation, okay. You can control the direction of rotation, controlling the phase phi of the wave you are sending, okay. You can control the angle you rotate by controlling the amplitude of this amplitude here of the pulse, okay, and the time you apply the pulse, okay. So pulses are rotation, okay. Pulses are gates, quantum gates, okay. So, and of course, you can implement much more sophisticated things, okay. For example, in quantum thermodynamics, usually you need to apply some evolution, some complex evolution like this. For example, you start from the initial Hamiltonian and change and drive your system through some path to a final Hamiltonian, okay. So you have to implement usually some very complex evolutions. So you can do this by applying different modulations, okay. So for example, you can apply a pulse, okay, modulated with an arbitrary shape, okay, and usually it looks like something like this, okay. The pulse, in fact, is a collection of small square pulses, okay, and each square pulse implements a field like this. So you have some amplitude, okay, and some phase, okay. So each pulse here is like this one here, okay, but with a different amplitude and phase, okay. So we can do this, okay, with many, each slice here has some amplitude, some phase, okay, and of course you can also reverse this, implement the opposite evolution, okay. So you have this here in the laboratory frame, but if you go to rotate frame, okay, the evolution of this shaped pulse here, you look like this, okay. You look like this. So the Hamiltonian, in fact, the evolution will be something like this, okay. So let me show an example. For example, and we did in many experiments we perform here. So in many experiments you start from some state, okay, and start from initial Hamiltonian and have to drive your system to a final Hamiltonian, okay. The system should go through this Hamiltonian here, okay? You have to drive the system according to this Hamiltonian this. So to implement this, what we did is to implement a shaped pulse like this, okay? Change the amplitude and phase, okay? Change the amplitude and phase, you can change the change the amplitude, you can change this parameter here, okay? And change the phase, you can change this parameter here inside the cosine and sine, okay? So change the phase, you can go from X to Y, and change the amplitude, you can change this parameter here, okay? So this is an example of a process that you have implemented in many experiments. So we have, for example, here, in this paper here, implemented this evolution, okay, in the qubit, and you perform a process tomography, okay? So it's the process matrix of the evolution, and then you can find that using this definition of fidelity here, you can implement this evolution here with fidelity around 3%, okay? 3 and 7% for forward and backward process, okay? So, okay. And another thing, another important thing also that I'd like to mention is that you can implement RF pulses to implement gates, okay? But also we don't have a projective measurement in NMR, okay? And to simulate other non-unitary operation, you use a gradient pulse, okay? So you have your sample here and put your sample inside coils, okay? And these coils here implement a magnetic fields that change with the position, okay? So the magnetic fields here is a little bit higher than here, and here. So it spins in different position of the samples, magnetic fields in the different, with different strength, okay? So for example, if you start like this, okay, and then apply a pulse, you move the spins, okay? You move the spins to this position here, and they start to process around the magnetic field, okay? If the magnetic field is homogeneous, they will process in phase, okay? But applying a gradient like this, okay, because each spins you feel different field, they will process with different velocities, okay? And if you sum over the whole sample, okay, you raise the coherences, okay? So what happens in the density matrix is that when you apply this kind of operation here, when you apply the gradient field, what happens is that you erase the non-diagonal elements of the density matrix, okay? And usually use this to simulate different non-unitary operations, okay? But note that it's not real a non-unitary operation. In fact, it's unitary operation, but it's unitary in each position, in each different position of the sample. You have a different unitary operation. So the average over the whole sample looks like a non-unitary, okay? So it's a kind of, it's the way you can emulate a non-unitary operation on NMR, okay? So going further, so we can use this, for example, in quantum thermodynamics. You can use this, for example, to build what we call here the pseudo-thermal spins examples, okay? So for example, if you have a single spins, okay, a single spin system, you have the spins in the thermal equilibrium and apply some pulses. For example, by a pulse that is a rotation, okay? A pulse that is a rotation. And so you have this system here, You have this density matrix here, okay? So applying the gradient field, you erase the non-diagonal elements of the density matrix. So you want to end with a density matrix like this, okay? So you can neglect this first part here because it's identity, okay? You cannot see the identity, the signal from the identity in the experiments. So we have only the second part here is the only part you really see in the experiments, okay? So this part is diagonal, okay? But you can choose the theta, okay? Here, the angle theta, so you can build so you can imprint the population, the spin population as you want, okay? Change the this theta here, okay? So you can change the theta to correspond to some thermal states, okay? So this is how you build. In fact, this is how we change the temperature on the experiments, because when you usually want to see NMR experiments on quantum thermodynamics, okay, and when the paper says that the change in temperature, we see some graph, but they say that you have different temperatures. In fact, it's not the real temperature, because the temperature is always the room temperature, okay? Okay, so what is changing is this. What we are changing, in fact, is this simulation is what you may call the spin temperature, okay? And because T1, okay, the realization time T1 on MR is very big, okay, can be several seconds and maybe minutes, okay? So these states here, you stay for several seconds or minutes, okay? So it's plenty of time to make a lot of experiments doing this, okay? So these are just a small example, okay? If you have some doubt, you can ask Diogo, okay, about this, because this paper is very old. This is just an example. It's not related to quantum thermodynamics, but an example how you can manipulate the spins, the populations, and predict whatever you want in the state of nuclear spin. So this is the example of a ferromagnetic system, okay? So what we did here is just to calculate how should be the populations of, okay, of a sum of 3/2 spins, ferromagnetic spins, okay, and imprint these populations on the NMR system, okay. And later, if you want, you can use these populations to simulate whatever you want, or okay. So now I will show some experiments we have done, okay? So the first of all is this. Well, I'll show now how to make different ways to make quantum thermodynamics experiments with NMR, okay? Okay, the simplest things you can do is, for example, is trying to probe the statistical work, okay, of some evolution. So the idea is you have your state here, okay, initial state here, and you apply some evolution, okay. So this evolution here is this guy here, okay, this operation here, and this evolution here is implemented by a shaped pulse, as I explained before, okay. So the idea is that you have your spins, okay, with some with two energy levels, okay, and you drive your system for this path here. You end with this situation here, and want to probe how much is the work performed on the system, okay. So you can do this using this interferometric approach, okay. It was created by, I think, by Mauro and others, okay. So the idea here, okay, so we have two spins here, one spin is your driving system, okay, that you create in the pseudo thermostat. Okay, so you do using pulses and gradients, you can put these spin here in any thermostat you want. Okay, so again, for example, in this graph here, I want to show different temperatures. In fact, I'm this temperature here is the spin temperature I show here. Okay, not the real temperature. Okay, so here we implement in this spin here, for example, the carbon, you imprint the your thermostats, okay? And the second spin here, you usually as ancillary, okay? So with this scheme here, okay, measuring the average value of sigma x and sigma y, that in the experiment, it means measure on the magnetization of the hydrogen in X and Y, okay? So you can probe the work done by this evolution here. So this evolution is shaped pulse. Our other these are implemented by pulses, okay? And the controller, the gates are implemented using pulses and let the spins interact for some time, okay? So this example here. So you measure here, what you measure here is what is called characteristic function, okay? And from the Fourier transform of characteristic function, have the work distribution. Okay, this is the first thing you could do in an NMR, okay? So we have one spin that you imprint your system, you drive your system with some evolution, and the second spin used as auxiliary, okay? So for example, we did this also here in this paper here. For example, if you start from some initial states and make the system involve, okay? If you involve with adiabatic according to adiabatic path, okay? So the system will be always on the equilibrium states, okay? So you go through this green trajectory here, okay? And the green trajectory always passing through the equilibrium states, okay? But if if the evolution has a finite, you implement the evolution in a finite time, okay, you will not go through the adiabatic path, okay? So you're gonna end up with a different states here that's not in the equilibrium state, okay? And this is for the backward. So associate with this non-adiabatic trajectories, there is a creation of entropy, okay? So if you recognize the creation of entropy, sigma, okay, is can be related to the probability of work, okay, of the forward and backward process. You can have, you can also prove the entropy generation, the distribution of the entropy generation in this path, in this evolution here, okay? So PFPB is what you measure here, okay? Is the work distribution, okay, for forward and backward process. So these experiments is essentially the same as before, but now you're looking to this quantity here, sigma, okay? And of course, if you can implement this evolution a little bit faster or slower, okay? And if you go fast, for example, it's the evolution, the total time for evolution is 100 microseconds, you create more entropy, okay? And if you implement slow evolution, you create less entropy, okay? And also you can see here in this graph here, this is the representation of log sphere. Okay, the green here is the adiabatic path. Okay, so for 100 microseconds, you can deviate a lot from the adiabatic path. Okay, but if you implement your experiments slower, then you are closer to the adiabatic path. Okay, so we can also probe the heat, okay, distribution of heat. Okay, in this experiment here, you did this, for example, using 3. Now you have using a system of 3 qubits with this molecule here, where this fluor atoms here, okay, are the qubits, okay. So again, you have one ancilla, okay, with you. This, for example, this fluor here can be our ancilla, okay, to probe the characteristic function. So you have your system here, okay, that you also can prepare in some pseudo-thermal state, okay, and you have this another system here called the reservoir, okay. So we implement some operation here. For example, this operation could, for example, entangle these qubits here with this, okay, the reservoir with the system, okay? Because if you entangle 2 qubits, okay, you are erasing information of the system, okay? You're erasing information. If you're erasing information, you have some heat associated with this, okay? So these experiments did this, okay? So you prepare this in some state, you have the reservoir, okay? And you will apply some operation here, for example, to entangle these 2 states here, 2 systems here, okay? And during the entanglement, the information is erased here, and we have some heat associated with this, okay? And this circuit here, you probe the distribution of heat associated with the erasing information of the system here, okay? So, for example, a typical characteristic function, you have a measure, and the Fourier transform is the distribution of work, okay? So, okay, and another very nice experiment, very beautiful experiment you can also do is the simulation of thermal contacts, okay? So, for example, now I have again the chloroform. You have the 2 qubits of the chloroform, but now you prepare both qubits in some thermostates, okay? So I can prepare carbon in some pseudo-thermostates and hydrogen also, okay? So after that, implement this sequence of operations here, okay? These are rotations, okay? This means let the system evolve freely, okay? They are interacting, so they let them just evolve, okay? And apply some rotation and let them evolve again and apply final rotation, okay? What we have here, okay? If you take the whole operation here, okay? This whole operation here is equivalent to this evolution here, okay? So this whole operation here makes the system involved with this effective Hamiltonian here. And this Hamiltonian is given by this, okay? So we are here simulating some Hamiltonian, okay? Implement quantum simulation of some Hamiltonian. But the interesting thing is that this operation here, okay, is a unitary operation and acts on both qubits, okay? But if you make a partial trace, okay, if you look to the evolution only in one of the 2 qubits, okay, the partial evolution you're gonna see, you have a map like this, okay? So if you look to the evolution only on the carbon or only on the hydrogen, okay, the evolution will be given by a map of this, one map like this, okay, with this operator given by this, okay? But this is the map of the thermalization. This is the não é, esqueci. Amplitude damping. Generalized amplitude damping. This is a generalized amplitude damping map, okay? Okay, with gamma given like this, okay? So if you have your evolution from 0 to tau, okay, this you implement you simulate the thermalization, okay, of each qubit, okay? So what happens if you apply this, you prepare this in the thermostat, prepare this in the thermostat, okay? And then you apply this operation here, this operation, you simulate a thermalization between you both qubits, okay? Because the evolution on each qubit you look like this, okay? So we did this, okay, in the experiment here, okay? You prepare two thermostats, okay? Prepare two thermostats. So my total densimass will be like this, okay? The thermostat created here in the hydrogen, the thermostat here we have created in the carbon, okay? But also you can have, but also you can also add some term here, okay, in the experiment to that correspond to the coherence, okay? So we have the thermostat, but also can add some coherence between the both systems, okay? If this extra term here has trace equal to 0, it means that if you make a partial trace and look only to the system look only to the densimass of the hydrogen, the densimass of the hydrogen will be still a thermostat, okay? And the densimass of the carbon will be, again, will be still a thermostat, okay? So we did the experiments to simulate the thermalization, okay, of this two system here. So if you have no coherence, you have this two the blue dots here, okay? So we have spin A, it's hydrogen, okay? It's in a hot state, okay? So if it starts, if they are not correlated, okay? So the spins, both spins start to have, we simulate the thermal contact, okay? So the energy, okay, of the internal energy, okay, of the hydrogen you decrease, okay, because it's now in a hot state, and the internal energy of the carbon you increase because it's a cold state. So we are simulating the thermalization, okay? When the heat is flowing through the cold, the hot to the cold, okay? But if we introduce some correlations, you can see this effect here, that the system that is already hot can heat even more, okay? And the system that is cold can cold even more. So the energy goes from the cold to the hot system, okay? Okay. So can also, using this kind of system, can also implement some thermal machines, okay? Again, you have the chloroform molecule, okay? We have our two systems here, the carbon and the hydrogen. We can prepare the carbon in some thermostats, the hydrogen again, okay? So you can implement the equivalent of the Otto cycle, okay? So in a quantum state, so the Otto cycle, you have some expansion of the gas, then you put heat on the system, then you compress the gas, and then you remove heat from the system, and this is the cycle, okay? So here, the cycle is you have a spin on a magnetic field, okay? You drive a system through some Hamiltonian to expand the gap, okay? Is this operation here that you do this by implementing some shaped pulse, okay? As I showed before. So here is the moment that you have to give heat to the system. So what you do this in the experiment by simulating the thermalization again. So you implement these states here, okay? This is our drive of system, our working system, okay? And the hydrogen you work as a reservoir, okay, as a bath, okay? So in the carbon, we apply the Chevrolet pulse to simulate the expansion, okay? And then you simulate the thermalization of the hydrogen to simulate the heat contact here, okay? The contact with the hot reservoir, and then we apply again the backward operation, okay? By implementing the shaped pulse, again another shaped pulse, and this is the complete cycle, okay, of the Otto cycle. Okay, so we can implement this. We can characterize the evolution. Okay, so also we can characterize this. Can also perform some state tomography. Okay, at the end or in every part of the circuit here, so I can calculate how much work you'll be extracted and the efficiency and things like that, okay? But very interesting also is that because you can do the same experiment here, okay? You can do this, okay. You can do the same experiment, but you can prepare, okay, because you can prepare this states here as I want, okay. I can prepare this state here to equivalent negative temperature, okay. It's just to invert the populations, okay. You have a population like this. If you invert like this, you're gonna have a equivalence of negative temperature, okay. And then you can simulate what would be an Otto cycle, okay, machine working with a reservoir at a negative temperature, okay. That's what we did here, okay. Thaisa did this, and if you have some question, Thaisa can answer, okay. If she not answer, then you don't give that job to Thaisa, that Ivan. Okay, but if she answer very well, then we can have a job. Okay, okay, let me help you to. Okay, oops. So very interesting is that when you put negative temperature here, okay, the efficiency of the cycle can be bigger than the classical efficiency that you have when you have the system only work with positive temperature, okay. And also, I think this is the last thing that you show, okay. You can also simulate thermalization in this system here, okay. It's more like a real system, so you have Thais also did this, so Thais also can answer question about this, okay. So we have here we have a solid state, okay, system. It's called here use this system called a Damantan. Okay, it's a very simple system on NMR also. So you have carbon and hydrogen. Okay, so it's a solid, and so you have some. Basically, you have some carbon atom, okay, surrounded by many hydrogens, okay, and they are coupled, and the nuclear spins of the carbon here are coupled to the nuclear spins of the many different hydrogen here through the dipolar interaction, okay. So the spins which are very close to the hydrogen, the interaction is stronger, okay, and the spins that are more distant, the state of interaction is a little bit lower, okay. So the Hamiltonian system, you look something like this, okay. So this is interaction of the carbon spin with the external magnetic field, okay, and this interaction of the carbon spins with many different hydrogens, okay. So here you have a system that is more, I think it's more real because it's more like a spin, okay, interacting with a bath, okay, because we have a large amount of hydrogen interacting with a single carbon, okay. So what you can do here, for example, is also simulate thermalization in this system here. If you look to this Hamiltonian here, okay, you have only Z terms here, okay? The spin operates only on the Z terms. So this Hamiltonian here, in fact, what they did to the carbon spins is to induce decoherence, okay? So the nuclear spin of the carbon here relax very fast because this interaction here, okay, this interaction here induces decoherence on the carbon spin, okay. So, but again, if you apply sequence pulses here, okay, that's very similar to those I showed before. So you can engineer this interaction here. So this interaction here, okay, you look like this, okay. So with this evolution here, you're gonna simulate the evolution of this Hamiltonian, okay. So now we have Z terms, X terms, and Y terms, okay. So what happens now that the effective evolution between the all those hydrogen here and the carbon, okay, you look like this, okay. But this can induce thermalization, okay. So doing this, we can also simulate thermalization on the system, okay. So what we did is, for example, to apply the sequence, okay, and we did some again we did some process tomography, okay, and you showed that the process matrix you have is a process mass of the thermalization map, okay. But what you show here that's very interesting is that, okay, if you only apply this, okay, the operation will have this process matrix here. This process mass, that's the process mass of the thermalization map, okay. But if you also invert the population of the hydrogens, okay, the hydrogens is the best, okay. So before start this simulation here, I invert the population of the hydrogen, okay. So I invert the population of the hydrogen and apply the sequence for simulation, okay. So what we found is this map here, okay. Only just path change, but this is exactly the thermalization map, okay. This thermalization map but with negative temperature. Okay. So what happens is when you do this, okay, the carbon spins will thermalize with the hydrogen spins. But if I invert the population of the hydrogen spins, that it's equivalent to put the hydrogen spins in the negative temperature, okay, the carbon spin will thermalize to to the temperature, to the negative temperature also, okay? So so this, for example, is show here, okay? So for example, if I prepare the carbon spin with magnetization down, okay, and simulate the thermalization, then it goes to the positive direction, okay? But if I invert the population of the bath, okay, the population of the hydrogen, okay, the carbon spin will thermalize to a negative direction, okay? So it means that we're simulating here the thermalization of positive and negative temperatures. So now so I have good news for you that you can go to the coffee break early, okay? Because it's so everybody can awake. So that's it, and these are some sites you can find more information, okay? And thank you very much.
Alexander, for the nice tutorial. So I think actually, I mean, you can go to the place where there is the coffee break, but I don't think there is going to be a coffee break earlier than it's supposed to be. But you can also just chat a little bit here. And I mean, that's also the thing. I think you wanted the conference to be as informal as possible, at least as I wanted. So let's just try to have this all the moments we can have just to discuss physics and all these things, okay? So if there is any other announcement? Oh, well, yeah, sure. If you have questions. Here.
Thanks for the talk. I was wondering if I understood correctly, you can fully characterize with your work distribution in your system, but can you actually harvest energy? Can you actually perform work for a useful task somehow, or can you just characterize the statistics?
I think it can. In those experiments, you are just characterizing how to perform, how to use that work. I don't know.
Because I think it's an open question in quantum thermo, no? If you can actually use this work, or it's just like foundation.
At least in this kind of experiments, maybe it will be difficult. Maybe in another system, maybe.
I don't know if I can ask another question in case.
We have plenty of time. I mean, you can back to you later. Yeah.
Hello. So I was wondering about when you simulated the thermal contact of 2 qubits, you had this density matrix that had the eta term, I think. It was basically the coherences, and you said when the trace is 0, but I thought it would always be 0 because coherences are essentially off diagonal term, right? So I didn't really understand like how, like you said you wanted to assure it was 0.
Yeah, you're right, because if it's only coherence, then the trace will be 0. Yeah.
Oh, so that's it.
Okay.
So there was.
I'm just saying that because it's also a thermostat. Because this is an extra term, okay? I'm just saying that this extra term should have trace equal to 0 to be only coherence and to represent only coherence and not, okay?
Okay, thanks. And just other thing about the, like, how close can you get to thermal equilibrium actually? Like, it is like really thermal equilibrium. And how long does it take?
This stage here, I mean, eh?
Yeah.
They're very, because you can, okay, you implement this with pulses, and okay, and you can do very precise operations on NMR. Okay, so these are very close. I mean, only for just one qubit here, or then just one spin, okay, the precision can manipulate the spins very good. So the fidelity, if you make a state tomography here, the fidelity will be 99.99. Will be very close, okay? And so it stays there. The realization time, the important realization time here is T1, okay? T2 is the realization time that use the coherence, okay? T2. T1 is the realization time that bring the system back to the thermal equilibrium, okay? So the important time is T1. T1 in liquid state NMR is 7 seconds or maybe minutes, okay?
Thanks. That's a lot.
Yeah, thank you. In your last slide, your thermalization process looks like non-monotonic, right? Isn't that true? Because thermalization by Lindeblum equations usually give monotonic behavior, but your thermalization process looks like non-monotonic. So is there any non-trivial reason or?
I don't understand very well, but what we did here, okay, we implement this simulation here, okay, for some time, okay. So after you can implement the process of any time you want, okay. So you simulate for some time to wait the system to real thermalize, okay, and then in this final time, this process matrix here, okay, is related to the process matrix you get here when this time here, for example, is much bigger than T1, okay. Okay. So it's these two process matrices here, okay.
Okay, thank you.
Okay, hi. Very impressive work. Thank you very much for the talk. I have just few simple questions. When you explain the way you implement a time evolution, my understanding is that you're doing a trotterization, right? I mean, you're breaking.
Yes.
So I wanted to understand if this is a source of error. When you explain it, you also showed that the fidelity was of the order of a few percent. I was curious to know if this error was due to the trotterization, to the fact that you have trotterized the Hamiltonian in the time evolution.
I mean, because you have this is trotterization, okay?
Yeah.
Okay. But also, I also show this fidelity here.
Yeah, at the very beginning you
The
were
very beginning,
discussing. Yeah,
this,
this one. So I
uh,
wanted to know if this was due to trotterization or something else.
I think it's more like the experimental imperfection, because this is a little bit different, huh? Because to implement this, you are implement a shaped pulse like this. So it's a lot of things like this, okay, putting together, okay. And I think the error will be more this error aqui, the most part of this error here will be you due to the experimental implementation. Okay, and also you can see that the backward, okay, is bigger than the forward, okay, but the way you
Characterize would be
it
the same.
is the same, okay. Probably is because, okay, you have to, because it's this here, okay, you start from the amplitude increase linearly, okay, so you start with few, if a small amplitude, then the increase, okay. The backward is opposite. You start already in the big amplitude and decrease, and this for the electronics is more complicated because you have a big shot in the beginning, okay, and this causes more problems because most of this error is sure because the experimental things.
And thank you very much. I have another question in relation to the way you implement the initialization when you want to thermalize your system. So you have this gradient field, you have an average that is over space.
Yeah.
A very simple question. Then you do your actual dynamics. So during the dynamics, do you keep this
No.
So
You just it's just I implement this just to erase the coherence. Okay, after that they are already after you erase the coherence, then you turn off this gradient fields and the system is already in the.
And then the question is, however, when you measure, I mean, your average is over space, so your way of measuring will always be over space then.
Yes. You are measuring the whole sample. So we have an ensemble, you are always measure the whole sample.
Thank you very much.
Morning. In pseudothermal states, how you change the effective temperature or spin temperature experimentally?
Just change the populations here. Okay, I have to calculate. I want to create some thermostate here. Okay.
Yeah.
So I know the Hamiltonian, how I know the temperature. So I know the population they should have. Okay.
So it's only change the number of particles in your system.
No, change the population. Change the population. This population here. Okay.
So what is the quantity that you have to change in the lab for change this quantity? This is my question. It's the magnetic field. It's what?
Here it's the you apply some gates here, okay? You apply some rotation, okay?
Okay.
So this rotation change the population of the spins, okay? So this is the density matrix, okay? So this means the population of spins up, population of spins down.
Oh, okay.
So if you apply some rotation here, okay, you can rotate your system, okay? So you can change these populations.
So for example, if I put a lot of spins up, I have a more larger effective temperature, something like that.
If you have all the spins up, for example, here you are simulating the zero temperature, for example.
Oh, okay.
You are simulating a pure state.
So is this temperature that you can put as negative?
Yes.
Oh, okay.
And then you can change this the way you want, okay?
Oh,
because
perfect.
you have a very precise control here, okay? And you can implement rotations from zero to pi. So you can implement this 1, 0 here. It's like zero temperature, okay? We can invert here, okay, 0, 1. You can implement do this like a thermostate. You can put 1/2. It would be infinite temperature, and you can do it. Okay.
Oh, nice. Sounds fun. Thank you.
So the coffee break will be late now.
You can blame me for the coffee break being
Okay.
late. So just going back to the question about thermalization and the fact that you're taking off the tilted gradient field. So if you take it off, as a sudden quench. In principle, your system doesn't change your state. Is this what you do? I mean, because you are switching off a field, and that in principle would change the state of your system. So how do you ensure that your system indeed remains thermalized, remains in a thermal state? I don't know if I'm explaining myself well, but
No, I mean, you turn off and turn on, turn off the gradient, okay?
and you do it very quickly, I suppose, so that your system doesn't change state.
I think I understand.
I'm a theorist, so I have in mind the sudden quench, you know, you the
I think
sudden
I understand.
quench the system.
I mean, you mean that during this evolution here, during this time, the state will evolve.
What I mean is you're thermalizing your system using your gradient pulses.
No,
okay?
not the
No.
gradient pulses.
The gradient field, you're thermalizing your field.
No. Yeah, but only to prepare the initial states. Okay.
Exactly. Then you turn off your field.
Yeah.
And when you
But-
turn off your field, how do you ensure that the act of turning off your field
But-
does not change
yeah.
your system state?
The gradient, you change the system because you erase the coherence, okay? But because you want to erase the coherence, okay, you don't care about the evolutions because they will only erase the coherence, but they will do nothing to the populations. And at the end, you are only interested in the populations.
Sure, we can maybe discuss later.
okay.
It's we can
Okay.
discuss.
We still have like 9 minutes, I mean.
Thank you for the talk. I was wondering, you always talking about 2 qubits. In treat one of them like a reservoir. Why can you treat them like a reservoir in the terms of free grounds of liberty? I don't know how to say that in English.
Yeah, because you mean that the what? Cadê? He was trying to explain, but I didn't understand that explanation. What is the? You mean this? Okay. You mean this? Well, I'll explain more or less the experiment here. Okay. The idea is to have your system, okay, here, and have another auxiliary system. So you untangle the system, okay, this with this, okay. This means that you are erasing information, okay, and together with the process of erasing information, you have some heat. How do you say heat? You can heat your environment, okay, if you erase information, okay. So the idea is to, and this, okay, this circuit here, okay, this interferometric circuit here, this is used to probe heat given to this system here, okay. So if you are simulate some erasing information here, okay, it means that some heat will be given to this system here. And the whole thing here, what the whole thing here does is to probe how much heat is given to the reservoir here.
But you can call in fact a reservoir because it's another qubit.
Yeah,
Right?
it's another qubit, yeah. So like this, it's a for example, it's like this, okay? You have 2 qubits here, okay? So we have to give heat to to the qubit, but you are giving this by doing this simulation here. So this is another qubit. So it's not really a reservoir. Okay, you can see that temperature is not really temperature, reservoir is not really reservoir, and the things are not okay. But what you can do, the referee is accepting and accepting this. So, but this looks like a reservoir. This is like a reservoir because this is a one spins interacting with 100 of other spins. Okay.
Maybe, I mean, okay.
Hi, Alexandre, thanks for the talk. I was curious about when you mentioned in this experiment a thermalization with a system at negative temperature, because normally systems at negative temperature, they want to lose energy to raise their entropy. And so if you interact a system of negative temperature with a system of positive temperature, you never thermalize with the system of negative temperature. The energy always goes to the and you always thermalize at positive temperature. So how did you manage to thermalize something at negative temperature? I didn't understand that.
If I understand, but in fact, I don't know, but maybe it's because the realization time is T1 is too big. So when you put, for example, this spins here, the hydrogen on the negative population, okay, it stays there for a long time, much bigger than the time you implement the experiments. So of course, when you put in the negative temperature, after some time, they will lose the energy and go back to the normal temperature, okay? But it's too big, okay? All the experiments is performed in a time very, very, very short than this time, T1, okay? So at the end of the experiment, when this guy here, when the hydrogen here thermalize, or when the carbon here thermalize, okay, the hydrogen are still, the hydrogens has hydrogen bath, okay, are still on the negative temperature because there's no time to hydrogen to thermalize yet.
But the carbon is also at negative temperature? No.
The carbon is your system. So
Yes.
I'm simulated the thermalization, the carbon with the hydrogen.
Yes.
So, okay, the carbon, I can start with the normal temperature, okay? And
But you're saying that at the end, the carbon is also at negative temperature.
the carbon spin is inverted, yes.
Okay, that sounds like violating the second law as well. Okay.
No, because I think because your T1 is much shorter. But if you wait some more time, then everybody will be in the positive again. Okay. Thaisa can explain.
Hello. Hey. So I was wondering about the like creating and destroying correlations.
Mhm.
Like when you create correlations, you are creating or losing information, and does it like take heat or dissipates heat?
You
What
create
happens
correlation, I
exactly?
think I'm not, don't know, but I just correlating two things. Don't know what do you mean.
Oh, sorry. Creating entanglement. You had the
Ah.
2 qubits and the ancillary qubit.
If you have two qubits, okay. If I correlate them, you have entangled the two qubits, okay?
Yeah.
If you look to the partial trace of one of them, then you lose information because, for example, you have a pure state here, okay? If you correlate them, okay? If you entangle them, if you look to the state of one qubit, only you'll be not anymore in a pure state, you'll be in a mixed state. Then you lose information.
And like you said there was a heat associated with this.
Yeah, as a Landau.
But does it
Landau.
dissipate heat or absorbs heat?
No, it's, the process of erasing things dissipate the heat.
Thanks.
Landau principle.
Okay.
Alexandre, thank you for the lecture. I was wondering about something about regarding the qubit reservoir. Do you have like intrinsic non-Markovian things like effects? Because the size of the reservoir matters, and I can imagine you doing what is the time of coherence like or correlations is it different between the the system and the reservoir, or is it like the same? Can actually remaking my question, sorry. Can you do Markovian things without worrying about non-Markovian effects?
If you can simulate some non-Markovian
No.
effect,
Can I rest assured that my simulation will be fully Markovian and everything will be like I will have no memory effects and so on if I want to do a simulation with NMR and so in the molecules you showed here.
I don't know exactly how to answer, but you have already did some experiments to simulate the non-Markovian effects. You have already. It depends how you do the experiments. Okay, I think in those experiments you show here, I think you don't have this issue here.
Okay, maybe now we can discuss. I mean, we should discuss in the breakfast. Maybe I also take the opportunity. I have the microphone. I'd say that the questions you made is not only for Alexandre, but as you said, for the whole community, because now we have a bunch of mathematical measures of work. You have a zoo of them already, but the physical question, what did this work really useful for? Knowing usual thermodynamics, this is, actually even a principle, which is work is a useful thing, but in quantum thermodynamics, I think this question is still clearly open, how to define a work that is useful for something besides publishing papers. Okay. Okay, so let's go to breakfast.
Tá. Oi, testando. 1, 2, 15. 129. 1.318.419. Não, estou testando.
Tá tudo bem, você
Tudo
tá com
bem.
o microfone ligado, João.
Não, vamos começar a discutir umas crises especiais que eu tenho tido.
Tem broadcasting no YouTube, né?
Quem que eu? Não, depois. Não? Ah, Caio. O Caio já colocou. So let's go back from the coffee break and start the new session. Now we are already late. So I also would like to say that for the speakers, it's better if you have a pen drive with the PDF or you send us the PDF or for a presentation to use the system here. If you want to use your computer, you can do it, but then you ask you to enter in the Zoom to post your presentation in the Zoom such that you can transmit in the YouTube. Okay, so you can use your computer, but then you have to log in the Zoom. We're gonna give you the room number, whatever, but it's best if you give us the PDF. So I think it's so. Now we have the pleasure to have Marcelo here to talk a little bit about how quantum thermodynamics can lead to new quantum optical resource. Okay, thank you, Marcelo.
So I have to press here.
Yeah, just start it. No, reset.
Yeah, I was going to press the wrong button on purpose, but never mind. Okay, so thank you very much, Thiago. Thank you, the organizers, for having me here. And so I'm Marcelo França Santos. The França is the F that is hidden there. I have many surnames, so I'm now marketing paleólogo because I went to Greece in January and I reconnected with my ancestors. So now I'm marketing paleólogo, but I'm Marcelo França Santos, as you know. Anyway, and I'm going to talk about how quantum thermodynamics leads to new quantum optical results. And the title of my talk has two motivations. The first one is personal. It's because I've been working on quantum optics and quantum open systems for a long time. And so I'm kind of, let's say, connect to the quantum thermodynamics community, but actually I come from quantum optics and quantum open systems. And the second motivation is actually because this is kind of an answer to a question that I'm asked many times. And the question comes from the following point, and I'm saying this because there are many new people in the audience, young people in the audience, so it's kind of a message to young people. Whenever there is a new trend in physics, it's very common that like young people rediscover the wheel, okay? And they do it, and they kind of recover results that are old for other communities. It's happened with quantum information, and I was already a quantum optician when quantum information gained momentum. So I've seen it happening with quantum information, and lots of young people and some old people as well, recovering quantum optical results and quantum open system results with quantum information language. And it's happened again with quantum thermodynamics. And sometimes people are criticized for doing this, and I get the criticism. And sometimes they are right when they are criticized. But sometimes you have to see it from a positive perspective, and that's what I want that's the message that I would like to convey today, is that there is also a kind of positive perspective in rediscovering the wheel. And the positive perspective is that when you approach the same type of problem with a new language, or with new questions, or with a different, fresh, new approach, you end up eventually finding new results that can be interesting. So that's the bottom line of the message that I want to convey today. So I don't need to say this to this audience, but I'll say it anyway. Quantum thermodynamics, there are many different approaches for it. And it can relate to how thermodynamical laws
applied to quantum systems and how to observe them, fundamentals of thermodynamics, tests of thermodynamics at quantum level, differences between classical and quantum systems, and so on and so forth, okay? And these are all problems that are interesting to tackle. These are all problems that are interesting to discuss. And this is kind of the language that we are seeing nowadays within the realm of quantum thermodynamics. And I used brackets for quantum because sometimes we are actually discussing classical thermodynamics of quantum systems, and sometimes we are doing something more than that, and in which case I think it's fair to say that we are doing quantum thermodynamics. But nevertheless, even when we are doing classical thermodynamics of quantum systems, is still interesting, and there are still many open questions related to it. So this is like it's a brand new field. Well, kind of. Anyway, it's not as new as people think. And my talk is related to this, is the fact that it's a little, anyway, we will see. So, and when we talk about thermodynamics, classical thermodynamics, obviously, one of the main issues is how you exchange energy, how you transport energy, and how efficiently you do it, how reversibly or irreversibly you do it, and what can you do with this exchange of energy between systems, physical systems, and one can claim that like one of the most important aspects is how you turn incoherent energy into coherent one, into work, and also how you turn incoherent energy into information, coherence here in the sense of information. And this is obviously a classical thermodynamic problem. And when you turn into quantum thermodynamics, you can still, or thermodynamics of quantum systems or quantum thermodynamics, you can still ask this kind of question. And so the transformation of incoherent energy into coherent energy relates to a very old problem, and it's been studied in respect to masers and lasers. And that's basically the essence of a laser or a maser, right? Is you pick up incoherent, an incoherent source of energy, and you turn it into a coherent source of energy that can be used to do so many things that like I'm not going to discuss here what a laser can do, but like you all know. But like when it comes to quantum systems, you can also turn incoherent energy into quantum coherence, right? So that's what happens, for example, when you condensate a Bose-Einstein condensation, when you condensate a cloud of atoms, for example. You can also turn incoherent energy into entanglement. Okay, so basically, when you go into the quantum realm, there is quantum information that you can exploit as well. So but it's still somehow, it's still, those are all kind of thermodynamical processes anyway. It's still using some source of energy to produce something else, either another type of source of energy or some information or some quantum information or whatever. And so just to say how old this problem is in quantum optics, for example, okay, that's the basis of laser cooling and trapping, which handled the Nobel Prize in 1997 to these three guys here. And the essence is that you have an atomic beam, which is hot, right? And you shine laser, so you can call the light that is being absorbed, you could call it work if you want. You're shining a coherent light that is absorbed by those atoms. Oh, sorry. How do I come back? I'm done. Thank you very much. Can somebody help me on? Yeah. Which one? Ah, okay. Ah, okay, so now you all know what I'm gonna say, so questions, please. Okay. Sorry about that. So anyway, so you can you absorb the light that is coming from the laser, you dissipate it, and then you cool down your sample. So laser cooling is an example of a thermodynamical process in quantum optics. You can also select velocity, and you can reach very low temperatures, and the limitation here is basically the line width of the atomic absorption, but then you can reach even lower temperatures with Sisyphus cooling. And again, you can also cool trapped atoms, and again, a Nobel Prize in 2012, because you can cool trapped ions. You can select velocities for cavity QED experiments, again, a Nobel Prize in 2012, basically because you can select velocities. So those are all thermodynamical processes that help you foster quantum information, help you to achieve new technological goals. Okay, so that's how you connect, and like turning more into what the quantum thermodynamical community has been used to. There has been, for example, a lot of questions whether in the thermodynamical language you can charge quantum batteries using quantum effects. So charging quantum batteries is another way of saying that I want to give energy to a quantum system in general. Okay, and so it's been widely studied how fast you can do it using quantum resources. For example, using entanglement and coherence, can I speed up the process of charging a system? It's not that common to ask a different question, which is, can I do better? Can I charge more? Can I give more energy to a system using quantum resources? And the results that I'm going to show you go into this direction. So what we investigated is, can I use quantum resources to actually give more energy to a system? And that's how I connect back quantum thermodynamics to old quantum optics, because actually giving energy to a system in quantum optics is known as optical pumping, for example. Okay, that's a very old subject, optical pumping. In fact, it relates to something that Alexandre actually showed in his transparencies, and when we reach there, I'll make the connection. But so and that's when I say that, like, thinking about it from a different perspective can give you new results. So basically, because I was interested in understanding quantum effects in charging quantum batteries, I actually realized that we could use a quantum effect to enhance optical pumping. And that's the message here. And so I will discuss quickly standard isothermal optical pumping, which is the standard way to optically pump a system, the one that we are used to. Then I'll discuss unitarily driven optical pumping. It's another way of doing it, and this is the one that relates to what Alexandre was showing. And here in item 2 and 3, that's where I'm going to show that you can usually actually use the vacuum of a quantum field. So it's obviously a quantum effect to actually enhance the charging of a battery, and doing it unitarily, for example. Okay. So basically, so let's start. Optical pumping, usual stuff. Okay, so I'm gonna call my battery levels G and E of a 3-level system. So this can be anything, can be an atom, can be a semiconductor, extons in a semiconductor, in quantum dots. It can be, I don't know, all those solid state pseudo atom systems, NV centers, superconducting qubits, whatever, okay, and NMR, whatever you want to say, that is a three-level system in which you can do basically this process, in which you can pump energy to coherently to take level G into level I, which is the higher level. So you connect these two levels through a coherent source, and I'm gonna call this work. I don't want to go into the discussion of what's work and heat, but for my purposes here, let's call it work, okay? And then, and let's call it work because it's an external classical source that I'm gonna use. And here, the system can dissipate from I to E. And as long as the dissipative, so the whole system is described by adding this coherent term to my Hamiltonian, which connects level G and I, and adding the incoherent dissipative term to my dynamics through a standard Lindblad master equation. And so this term takes care of the dissipation here, okay? And basically, if you do this, as long as the decay rate here is much larger than the coupling constant here, basically you can eliminate adiabatically level I. So this level, the population of this level doesn't matter that much, except for what the comment that I'm gonna make here very soon. But basically, as soon as you get population here, it dissipates and comes to this level. So effectively, we can call this an effective two-level system. And I'm actually pumping population from G to E through level I. And that's a standard optical pumping process. I'm calling it isothermal because actually this reservoir that dissipates is at a fixed temperature. And basically, the equilibrium populations of the system has this ratio here, okay? And the reason is you still have a little bit of population in level I because obviously this dissipative reservoir can still give energy to the system back and repopulate level I. So you reach equilibrium when you reach these conditions here, and the reason you have this two factor here is because exactly level I can still be populated, and the larger the closer these two levels are, the larger the population of level Y basically. Okay, so that's the overall picture of standard optical pumping. And in this paper, I studied with my student the efficiency of doing this optical pumping scheme, which is something interesting. I mean, from a thermodynamical point of view, usually people didn't care that much about this, but like so basically we tackle this efficiency as a function of the difference of energy of these levels and so on and so forth. So this is a standard optical pumping. You can also exploit this as a heat engine. You just need to extract energy from this level back to the ground state. So then you close the cycle. So you have an effective heat exchange from level G to level E, and work extraction from level E to level G. And again, we studied again with my former PhD student and some colleagues in Italy that I'm sure most of you recognize. We studied the efficiency of this kind of cycle when we were, so basically when we were discussing the charging processes and the extraction of energy process. So this is still standard optical pumping, okay? So another way of optically pump is to do it coherently, and that connects to what Alexandre was showing when he inverted the population of the hydrogen atom in his reservoir. That was a coherent field that actually inverted population, okay? So that's what you do here. You have, again, a two-level system, and you can shine a coherent light here, for example, or an external force that drives the system from G to E, but then obviously it's going to drive from E to G. And the best that you can do in this case is to invert population. And if you invert population, the gain in energy that you're going to have is going to be, so this is like the initial state. I'm going to assume I have a thermal state. And so there is some thermal population in each one of these levels. And when you invert population, the gain that you have is the difference of population times the energy of each level. And then we can compare, okay, this unitary, and I'm gonna call it semi-classical charging, which is this unitary inversion of population here, with the optical pumping case that I was discussing before. And you see that there is going to be a gain. So here is the difference, and there's going to be a gain depending on the energy of level I, depending on the separation of frequencies from level I to level E and so on. Okay, so one process, and the reason is basically because this energy separation is going to determine the effect, the thermal population of each one of these levels, and this is going to affect how efficient each one of the processes is in giving energy to the system. So beyond a certain ratio of level I and level E of energy, standard optical pump gains from this population inversion, direct unitary population inversion. So that's the standard stuff. People have done it many times. What I'm going to show you from now on is an alternative scheme. And to discuss this alternative scheme, I'm going to quickly do some quantum optics here, standard quantum optics as well. So let's go back to our three-level system. And now I'm going to do the unitary transport of population from level G to level E through a different channel. This time, instead of a direct classical force, I'm going to use the combination of two classical forces through level I, but dispersively. So that means that these two guys, they never actually populate level I. Level I is just used as a virtual level to connect G and E. And so we have now two classical sources, two lasers, for example, depending on your system. That if these are optical transitions, then two lasers. And the combination of these two classical sources creates as long as I can, again, adiabatically eliminate level I, so as long as delta is very much larger than the coupling terms of these two lasers, I describe these dynamics through an effective Hamiltonian that has a dynamical Stark effect correction to the energies of level G and E, and has an effective coupling of essentially the same order of magnitude that connects level G with level E. So you see that like this implements, again, the unitary direct transfer of population from level G to E, which can charge my battery, if you want to say it in this way. And basically you get, for the difference of energy, after you've done the full cycle, full inversion of population, again, you get the same that you would get with the direct coupling. However, you see that, like, let's see what happens now if I change one of my fields from a classical field to a quantized field. Obviously, every field is quantized and so on and so forth. So what I meant by classical field is a quantized field, but in a coherent state with very large number of excitations, which approximates very well, especially for this kind of dynamics, that of a classical field. So now I don't want to do this anymore. I'm going to take into consideration the fact that my field is quantized. And actually, so basically, if I do it, if I consider that this field is quantized, so this one is still driven by a classical source, but this one is a quantized field, monomode field, I get the same kind of physics that I had before. Again, a dynamical Stark shift to levels G and E and an effective coupling. The difference is that my component due to the blue field depends on so the dynamical Stark shift always depends on the intensity of the field. But now the intensity of the field is quantized. So basically depends on the number of excitations that I have here, right? And again, the effective coupling also now depends on exchange of quantized photons with my quantized field, an exchange that actually correlates my system with this field. So that's basically the difference from quantum to classical in that sense, is that now I can create correlation, and now I have a quantized dependence on the number of excitations in the blue field. So it's the same physics, but with a quantized field. And after I include a small change of energy correction to levels G and E, and that comes from a static Stark effect, I rewrite this effective Hamiltonian in this way. And now it becomes clear what I'm going to do next, because basically what you see is that if you go to that Hamiltonian, you're going to see first that level E0 is an eigenstate of that Hamiltonian with eigenvalue 0, which means that like at level, so the joint state of the atom in the excited E state and the field in the vacuum does not move with that Hamiltonian, it stays where it is. So that's information number one, an important one. The second information that is important is that that Hamiltonian, similar to the famous James Cumming Hamiltonian, splits in doublets, but this time it is an anti-James Cumming Hamiltonian, in the sense that like I give an excitation to my quantum field and I excite the atom as well. The total energy to do this comes from the external classical source that I'm providing. Okay, so there's no energy violation, conservation violation, nothing like that. I'm pumping with a large photon that is converted partially in a smaller photon and a net energy flux to my qubit. But it's still separated in doublets. Okay, and the point is that now if you look at this, the tuning of the evolution of these doublets depend on the intensity, on the number of excitations in the quantized field. And so that's, I still get Rabi oscillations between my quantized mode and my atom, but now the tuning and the coupling depend on N. And I have basically two important regimes here, and they are going to depend on the ratio between the strength of my quantum coupling and my classical coupling. Okay, so keep in mind this R is the ratio between my quantum coupling and my classical coupling, and this is going to define the two regimes. And basically, the two regimes that I'm talking about are, one of them is the standard anti-James Cumming regime, and this happens when the coupling with my classical strength, my classical field, is much larger than the coupling with my quantized field, and that's easy to understand. If this happens, the Stark shift due to the classical field is much larger than the N-dependent Stark shift due to the quantum field. So basically, this N-dependent Stark shift due to the quantum field doesn't matter that much, and essentially all the doublets couple more or less the same with the same Rabi frequency, bare Rabi frequency, I should say, and that means that like we are in the what is known as the anti-James Cumming regime standard stuff. So if that happens and I turn on my classical field, every doublet is going to oscillate. That's the bottom message. So the other regime is what we call the selective regime. Okay, the selective regime is the opposite one, when my coupling to the quantum field is much larger than my coupling to the classical field. Now, what happens is that depending on the number of photons in my quantum mode, I shift level E enough to either put it in resonance for my transition or to take out of resonance for my transition. And that's where selectivity comes. So what I mean by selectivity is now by selecting the number of excitations in my quantum mode, okay, only one doublet is going to oscillate and all the other doublets remain where they are. They only gain phases. So I can now pick up the entire Hilbert space of my joint atom and quantized field and select which doublet is going to oscillate. Okay, that's the basis of the selective regime. But now if I look at this, so this was proposed by us, and that's what I mean by revisiting. This was proposed by us a long time ago in papers, results where we were interested in preparation of Fock states and reconstruction of the field state, or in the manipulation of the quantum state of the harmonic oscillator, okay? So in general. But you see that I was not worried about pumping energy into the atom. So I was actually using the atom to manipulate the quantized mode. And then we realized that I could do the opposite. I could use the quantized mode to manipulate the atom. And so basically the idea is simple. Now that if we operate in the selective regime, let's see what happens if I start with the thermal state of my atom and my field. So from a thermodynamical point of view, this is free, right? It's a free resource. I'm starting with the thermal state of my atom and my field. But now I'm operating this cycle in the selective regime. So what I'm going to do is I'm going to select, so I'm going to tune my resonance with that Stark effect, static Stark effect. I'm going to tune my resonance. So I'm going to choose my Stark effect of level G in such a way that only the first doublet evolves. And the first doublet picks up the atom in level G and the vacuum of my oscillator, quantized oscillator, and takes it into the excited state of the atom and one excitation in the oscillator. So only this doublet evolves. But now you imagine that like the vacuum of my oscillator is the one that is most populated. So by doing this, I have already managed to transfer a lot of population, atomic population from level G to level E, right? And because E0 is an eigenvalue of is an eigenstate of my Hamiltonian, coupling Hamiltonian with eigenvalue 0, state E is already there with the vacuum. So now population of G0 goes into E1. And the atom now accumulates population at level E, corresponding to population of the oscillator in level 0 and 1. And then what I do is I turn again. I change again the resonance condition to couple G1 to E2. So now I'm going to transfer population from G1 to E2. And again, I'm taking the second largest portion of population from the quantized field and using it to populate the atom in level E. And then obviously it's easy to see that if I keep doing it, if I keep transferring population, I end up transferring most of the population, atomic population, from G to level E, okay? And that's the basics of the idea. So to do this, I just keep retuning my system in each step of my evolution. So after I've done it many times, I can calculate the energy variation due to the process. And what I'm going to come up with is that, like, so the calculation takes me to the one that I would get if I did the direct semi-classical transfer of population plus something that is obviously strictly positive, right? Because that's the product of two populations. And if you see here, this is actually this can be actually the second largest population of the system as long as P0T is very large. And that happens whenever the gap of my quantized field is much larger than the thermal population of the system. If this is true, okay, then I basically transfer all the population from level G to level E, and that beats a lot my classical result. So here what you guys are seeing is that, like, so that's the variation of energy as a function of the ratio between the energy of level I and level E. So level I is the third one that I'm using just as a support system, a virtual system. And this is the optical pumping, isothermal optical pumping. This is the classical swap, and this is the vacuum enhanced swap. Okay, the one that I just showed. This vacuum enhanced swap obviously takes a long time because each one of these processes is slow, and I have to keep doing it for each one of the doublets. So that's a very, let's say, inefficient process from a time point of view. Okay, so an alternative to this is actually to do it as a single shot. But then to do it as a single shot, it's better to operate in the other regime, in the anti-Janus Cummins regime. Because then I want all the doublets to evolve together, and there is an optimal time that I have to calculate, usually numerically. I have to extract the optimal time to do the best transfer of energy, and that is due to the fact that, like, it will depend on the population distribution that I have, and this population distribution depends on the temperature. So for each temperature, I have to adjust the optimal time. But once I know it, and it's easy to calculate it, once I know the optimal time, then I do a single shot conversion of population, but then operating in the anti-Janus Cummins regime. Okay, and this single shot will have its efficiency as well, and it's all described in this paper that we published with this with my two students, Thiago, who is now a postdoc in France, and Johan, who is finishing the PhD with me. Johan is here, by the way. He's sitting there. If you guys want to talk to him, very nice guy. You should talk to him. Much nicer than me, by the way. Okay, and so this is the result that we get, and then with Felipe Barra and his student, Felipe in Chile, we actually extended this idea to operate this in a kind of autonomous way. So what I have shown so far functions for very well-controlled time steps. So I need to turn on the coupling for a specific time and turn it off if it's single shot, or worse, I have to do it many times if it's the ideal process. Here, what we have shown is that, like, you can turn it into a kind of autonomous pumping scheme, optical pumping scheme, in which you send my atom or my system through many of those oscillators, each one of them prepared in the same thermostat, each one of them coupled to the system in the same way. But now I don't care that much for the time of interaction. It can be a short time of interaction. I don't even need to control the time of interaction that much. Okay, and we have shown that nevertheless, if you do it asymptotically, your system will reach a steady state. This steady state will depend essentially on the energy of the quantized oscillator, and you see that the population of level E is larger than the population of level G, so I managed to pump energy anyway into the system. It's not that difficult to see that you reach this steady state. You just need to calculate, you just need to show that PGI is related to, so the difference between the PGI and this asymptotic state for PG gets smaller the larger the number of steps that you have. So basically you're saying that you asymptotically you are reaching that state. And this paper analyzes this from many other angles. We do the full thermodynamics of this process. We also do the thermodynamics of the reverse process, which is to use many atoms of this to pump energy into the quantized system as well. And it's a full thermodynamical picture, but obviously I wouldn't have time to discuss all this. But the fact, the take-home message is that you can also do it asymptotically and autonomously. And here I show a comparison of the four schemes that I have discussed. So here you have optical pumping, here you have the classical swap, the autonomous antigen scamming swap is better than optical pumping and the classical swap most of the time, and the vacuum enhanced swap is the one that tops everybody else. It's the best one. So I just, before I finish this presentation, I just want to mention that like there is another work that we're presenting here, which is going to be published in Physical Review Research very soon. And it's a poster that Johan is going to present, right? So if you guys want to discuss this with him or with me or with Fernando Nicasio, who is also sitting here and is also a much nicer person than me. Yeah, I am the worst of this group. Of this group. I'm not saying the whole room, okay? Just this group. Just to make it clear, okay? And in this work, what we discuss is like there is a well-known invariance of the Lindblad equation. Goritsky could have solved a Lindblad equation, and however, we showed that there are physical consequences that can be extracted from this invariance. So basically, you can have the same evolution for the state and still have different thermodynamics, and that's also something that I think is interesting to discuss. And this is actually very well related to what Thiago was mentioning, the difference of how we define work, heat, and stuff like that. Okay, so that's it. I stayed sharply. No, sharp. Sharp. There was a time delay between pressing the button and starting my talk. So sharp. So thank you very much.
So we have 5 minutes for questions and it's counting. So be quickly.
I mean, it might be a sort of illegal question given the very first slide that you showed, but just as a curiosity, did you check also for the various protocols how the power is affected by the various protocols?
How
the charging power is affected by the various protocols? Like the best one is also the best from that viewpoint?
So we have checked, so basically we have checked stuff like this as well. We have checked the efficiency of the thermodynamic efficiency of the processes and power that is input into the system as well. It's interesting because depending, so I can answer this in many levels. Okay, first of all, even for standard optical pumping, I had never seen it discussed. Like it is obviously a process in which you have to give more energy than you get, obviously. But then what is the best way of doing it? So we have discussed this. But when you come to the quantum enhanced process, the point is that you are actually storing energy in your quantized system as well. So there is an overall conservation of energy. So in that sense, obviously, we also studied the efficiency in terms of power. And if you talk about the best model, the ideal case, then it's a very simple calculation. And basically, whatever you can do it as long as you have level I slightly larger than level E, you can do it, and it works fine. So the amount of energy that you waste is actually very small. Okay. However, if you want to do it in the single shot, then the best situation is to have level I larger, much larger than level E. But that you have so the best way of achieving the result is the one that wastes more energy. So there is a trade-off. So again, in the ideal case, it's very slow, but you don't waste that much energy. In the not ideal case, from the result point of view, but from the thermodynamical case, probably the ideal one, then there is a trade-off. Okay, you need to spend more power to have a better result.
Is there a way to estimate the power? Because this is a figure of merit that typically used in the community of quantum batteries.
Yeah, so that's related to Dario's question. We did estimate the power for all these processes. So basically, again, it's related to, so you can count. You can count how many excitations you're putting into the system, and the excitation is split. So it's an overall energy conserving process. So it's actually very easy to calculate how much energy you have put into the system. Okay.
The energy, but the time.
Yeah. So time, again, that's the point. You can estimate for sure because you know exactly how much time you need to spend in each one of the transitions. Okay. I don't have the numbers with me right now, but yeah, it's very easy. Again, in the ideal case, basically you know exactly how much it has to last, each one of the transitions, and you know, so you basically sum all the times and you divide the total. But the point is that it's very easy to calculate. We have done it. You can check the papers. And I'm sorry to not bring the answer here.
I was curious if you can scale the system and show some effects of quantum advantage that was claimed in quantum batteries.
So quantum advantage beyond the use of the vacuum, you mean?
No, actually for power charging.
Yeah, okay. Certainly you can do this calculation. I'm not sure. No, this one we haven't done, but yeah, sure.
Okay, thanks.
Go ahead.
So one last quick question.
I'm very happy if you do it, by the way.
Thank you for the very nice talk. So you have this lambda system, you have one field that is still classical, the other is quantized. The next step could be to quantize also the other field. Have you thought about that? Would that give any advantage?
Yeah, so thank you for the question. Sure. So from the point of view of the main target here, so autonomously, it wouldn't work. Obviously, because then G0 becomes also an eigenstate with eigenvalue 0. So in the end, you don't move. You need some external power source. But then the question is, what if this external power source cannot be treated classically? So this is something that we are working on as well. Although obviously in quantum optics there have been, but not targeting enhancing of energy transfer and so on. So this is something that we are working on as well. Thank you for the question. But nevertheless, we have to remember that this would correlate the three systems anyway. So this correlation needs to be taken into consideration.
So let's thank Marcelo again.
Ó, 25, quando der 5, quando dá 5, ele avisa. Vou. Tem usar aí, falar que tem 25 aqui no final, do shopping. Também tem ali, e tem aqui no Manel, né, do outro lado do muro, que é barato. Manel, ninguém merece. Peraí, antes de começar, qual a dica aqui? Acho que é só compartilhar para lá. Ah, não, para cima.
Tem um pointer aí.
É, mas aqui ele vai para frente. Como é que vai para trás?
Vai deixando tudo. Clica para trás? Para baixo, para baixo.
Aqui? Ah, para baixo. Ok. Pointer?
Onde que é o pointer, Alexandre? Onde que é o pointer?
E aí? Ah, ok. Ah, good.
Okay, so for the last talk in the morning session, we're gonna have Caio Levenkopf from the Universidade Federal Fluminense.
Yes, I'm
So-
your colleague.
Okay, so thank you, Caio.
So thank you for having me here. Oh, this is the one, sorry. Thank you for the opportunity and to talk about this work. I come from a slightly different community, which is quantum transport of electrons. And as Marcelo said, described, I basically do thermodynamics of quantum systems. Sometimes I try to do quantum thermodynamics as well. So the main question here that I want to address is basically if I have a quantum system coupled to source and drain reservoirs, and the current is flowing through it. It's a non-equilibrium process. I would like to know what is the entropy production rate under different settings, and what is the role of quantum physics, et cetera, et cetera. So the field is quite new, but old in a sense. There are always, it's surprising that there is already a review paper in 10 years ago with very few experiments, but it captures actually what is done. So you have basically a quantum system, which is described by this guy here. You have a classical drive, which could be your bias or whatever. We are interested in electrons, and we can measure things as a function of time. We can actually measure heat current, charge current, and build some entropy, infer the entropy transfer between reservoirs. And one should not forget that sometimes sometimes not, that the system is coupled to a phonon bath. Good. So two experiments that I want to show here, it's not to discuss, but to show that this is not fiction. It's that nowadays we are actually capable the experimentalists are capable of measuring heat flow, the heat current, which is a very hard measure to be done. And we are usually used to charge currents and noise. And nowadays it's possible to do that. And with that, we can establish some connection to experiments and theory, because then we have everything we want. And this is a thing I'm kind of involved. It's nice too. So it's not related to entropy production, but there is a big effort on measuring the entropy as you approach zero temperature for different solid state systems. So this is a proposal which is very nice. Okay, so this is the outline of the talk. I'll just make a small introduction, flash the main elements I want to discuss with you, and then I'll go to the main results. So it's a short talk. Okay, so the first thing I want to address is, I'm concerned about small systems, nanostructures. So there is always this question of, are you doing quantum physics, or are you only doing physics of small systems? And actually, the thermodynamics of small systems has been discussed already a long time ago. And I'll just pick up this paper by Chris Jarzinski, where he flashes a couple of important things when you address these systems. The first one, which is critical for us, is that if you want to understand what is the energy contained here, what is the flow of heat, flow of energy, et cetera, you have to introduce some kind of partition to your system. And then as standard, you use your partition, you have a system, the environment, and the coupling. The problem is, if your system is very small, the coupling becomes very important, because the size of whatever the coupling is comparable to the system itself. And then you have all these difficulties in defining different quantities here. Other than that, when you have a large system, you don't have to deal with fluctuations, 1 of square root of n. But if you are doing with a small system, then there is a distribution of things. And eventually you get very surprising results, currents flowing to the wrong direction, et cetera, due to fluctuations. Usually the mean, they agree with the standard thermodynamic relations, but the other not. Okay, so what about entropy production? So this can go back to Boltzmann, but in condensed matter, in the bulk, we know very well what to do. There is a common language to address this question. You can formulate all this in terms of Green's functions. You can compute the local entropy density. There is a continuity duration, and you can actually, by applying a bias or a gradient of temperature or whatever, you can easily compute the entropy production for bulk. This is well established. Now, if you go to small systems, then you have a problem because that I already alluded to before. So suppose first that I'm deep in the quantum regime. So the coherence length, the electronic coherence length is much larger than the system size. And I have a small system. And then I go back to the same question. I need to introduce usually a partition. And that settles a lot of ambiguities in my system because I don't know what is the specific heat of the system, what is the partition, what is the environment, et cetera, et cetera. So there is a lot of arbitrariness in that. And then what a kind of, I mean, this is kind of experimental image, a setting given by my colleague, Charlie Marcus. And this is a quantum dot. I forgot to tell you what it is. So this is an actual system where you have the electrons in these blue regions. There are the stop gates, which are electrostatically coupled to, well, they are metallic, and due to an electric field, you can control the opening or the closing and eventually apply a bias in these two contacts. So this is genuine resistor, if you want, a quantum resistor, because it's small. At small temperatures, it's governed by quantum mechanics. And then here's a cartoon of the different regimes that you observe in transport in quantum dots. If the dot is wide open, then you push the electrons through it, and there is no obstruction because it's like a fluid. And then you see this nice fluctuations as a function, for instance, of the chemical potential, and they are reproducible, and they are due to quantum coherence. So these are resonances that eventually they superpose. In the other regime, the weak tunneling, then basically the dot is closed, and then you want to put another electron there, you have to pay a price. You have to charge it capacitively, and you have to pay this electrostatic energy. And then what you see is a sequence of peaks equally spaced. In the middle, there is a complicated regime that I won't address today. Okay, so we focus on that and that, wide open and closed. Okay, so, and then going back to the partition, if you do electronic transport, we showed a number of years ago, sorry, here. Yeah, we showed a number of years ago that the system doesn't care what kind of partition you introduce for the electronic transport. Partition-free or partition approaches give the same result. This is a rigorous proof for time-independent or time-dependent transport. And for, let's say, thermal transport, then you end up with the same problems that Brzezinski described in this old paper. And you have to choose some partition. And then there is a nice paper by a colleague of mine, Liliana Hachea, who very democratically splits the partition half inside the system, half outside, reproduces the laws of thermodynamics, but then in the average quantities, it's fine. But if you put a multi-terminal case, it doesn't work. And the fluctuations depend very much about how you choose this partition. And this was actually pointed out by this former student of mine. Okay, good. Let's move on. So partition is essential. So the idea is that we had to come up with a formulation that doesn't depend on this partition. And then we took, well, we used the very old results from Landau and Büttiker, which is the standard way to formulate transport in mesoscopic systems. And so it's essentially different from non-equilibrium Green's functions because in this formulation, what you have is that you measure the currents far away from the system, very far from the partition. So essentially, you formulate the system, the electronic transport in terms of the S matrix. S matrix relates to asymptotic states. And it doesn't matter how where you put your partition, you get the same results as invariant. And so we have to formulate all these thermodynamic relations in terms of currents that you measure and actually relate to what the experimentalists do that you measure far away in the asymptotic regime. And this is the trick, and this is what we described in this old PRL paper. Good. So now we are on business. So what do we learn from that? Basically, from thermoelectrics, old stuff, the entropy production is essentially related to a charge current and a particle current, and these are the let's say, generalized forces you want. So essentially, we reduce the problem of computing these currents, and this is what we do here. And then, okay, so there are a number of formulas. This is the way you describe in standard mesoscopics how you compute a current. It's an ugly integral, but if you take the thermal average, then things simplify, and eventually you end up with some relations that involve the S matrix, which is something you learn to compute in a standard course in quantum mechanics in 1D. And here we do it in a more elaborate geometry. And so you end up with formulas for the charge current, for the particle current and the charge current. And then the entropy production rate is related to that. Okay, so now we have a working tool to do things. How does it relate to the language that you probably are more familiar with? You can rewrite this formula in terms of some Shannon entropy, the flux of this Shannon entropy that flies out, that flows in, and some relative entropy. And this is the cute part. So you develop, once you shoot an electron inside the system and the propagation is fully coherent, it develops some correlations, it entangles, and when it gets out, it gets information about where he passes through, and this is contained, this is the quantum part of the whole thing. All the rest is just kinetics. And then you can generalize this. This is the average. You can generalize this for distribution, higher moments, and noise. And this is what we do. Then the coherent, the part that is related to correlations is noise. And basically, if you take an average, you measure, you measure a bunch of electrons flowing, and then you don't know the distribution time that they arrive. But if you have a good apparatus, you actually will listen, tick, 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 and then you know, you reduce the Wave packet if you want, and you know the distribution of times they arrive. And formulated as an operator, as you want to compute correlation, autocorrelation functions, current autocorrelation functions. And then you can compute the variance and different higher moments. And this is one of our results, is that we actually can compute the distribution of electrons that flow as a function of the bias and the temperature. And actually what is interesting is that depending on your system size, sometimes you put a small bias, the electron will flow back, and this is a result of this calculation. This is And you can relate this to the fluctuation theorem that has to do with all this, entropy thing. Now, well, it's a theorem you don't have to show, but if you have this nice agreement, you know that you are doing your calculations right. And then the second question is now how to ask is, what is quantum in this? What is the quantumness of this thing? And so we went to this thermodynamic uncertainty ratios, and there are a number of papers. This is actually what attracted us to that. There are a number of theoretical papers from this community going to that. And what we know is that in the weak coupling regime, you can map the transport into rate equations and Markov chains. And this is exactly the starting point by these guys to show this uncertainty relation. And what we actually know how to do better or improve is that we can calculate at the strong coupling regime these quantities. And we can show that depending on the coupling, you get a strict, you can actually prove that this phi is positive by rigorous calculations. And now what number of people found is that there are violations for this thermodynamic uncertainty relations when you address the specific quantum systems. And there are even bounds that predict that they can be large, but the numerics always see a very small thing. And what we have done is that we actually expanded the formal expression in powers of gamma over mu when gamma is small, when the coupling is small, or inverse powers when the coupling is strong. And we actually can predict what is the behavior in these two limits. And we know that the second correction is actually positive. It's not going like that, it's going like this, but the prefactor is very complicated to calculate, and it's very entangled expression. So we actually did this in a model, and actually we reproduced these results that people have seen in the literature. The violations are very small, but we can predict them when you know a model, we can actually predict at least the behavior here, not the upset in here. And we know that it's related to the gamma, this parameter gamma over the bias. And this is difficult to measure. So, but this is the quantum correction. Things. Unfortunately, it's small. Now, the second question I wanted to ask is, what happens when you actually introduce decoherence in your system? And this is done traditionally in our field by a model introduced by the late Marcus Büttiker, which is called Büttiker's voltage probe model. And then what you see is that what we learn is that actually then all these violations, they disappear. And the lessons from mesoscopics is that we know more or less how to compute this guy, and this is our technical development. And we show that the fluctuations reduce, and the phi is always tends to be bigger, and these corrections disappear. Quantum corrections disappear. So this is the upshot. And now, in the 5 minutes I have, I'll finish earlier. In the 5 minutes I have, I want to do something different. I want actually to present a problem which is open, and I hope that somebody here can contribute, and then we can do something with respect to that. So it's related to that, but it's slightly different. So I want now to discuss the entropy production. All this has been discussed in this scenario where I have single particles flowing in the system. This is good when the interactions are not strong, when I have either Coulomb blockade in the vicinity of the resonance, it's forcing a little bit, but interactions are not, I mean, they enter in a different way, or if you have an open quantum dot. That works nicely, and people are using this Landauer-Büttiker formula a lot. But there are situations where it doesn't work, and interactions are important. eventually you lead to correlated systems. I'm sticking to the mean field, and let's go to that. So it's almost one little step beyond what I talked to you. So what we learn in our quantum mechanical classes is that if I have a system, an interacting system, and I want to understand the equilibrium solution, I always resort to a minimization principle. Fine. Okay. And for instance, the free energy or the total energy. And the numerical implementation, for instance, could be this famous Hartree-Fock equations, where I start with some educated guess for the eigenfunctions and eigenvalues of my system. I check what is the expectation energy or free energy. Then I solve the Hartree-Fock equations. I generate again, and I do it, a self-consistent solution until this guy converges to a minimum. This is something that, it's in all these textbooks. Now, if I'm not in equilibrium, then I have a problem because there is no minimization principle. Well, but there is a numerical implementation. People know how to solve things. And basically, if you start, for instance, with the traditional non-equilibrium Green's functions, then if I start with an educated guess for the charge distribution in my system, I can construct the Green's functions, and I do it out of equilibrium several times, and eventually I keep asking myself if it does converge. Fine. So then you ask me, why are you worried? So there is a recipe. Well, there is a recipe, but in equilibrium, we know that these self-consistent solutions, equations, they are nonlinear. And normally you have, frequently you have many minima in your system. And then having this idea that the minimization principle, the recipe is based on the minimization of some quantity, variational, then we have to check which one is the one that you discard the local minimum and you choose the global one. This is the one that is the one that you're looking for. In non-equilibrium, there is nothing to minimize. So if you have many minima, then you end up with a solution, which one you pick, right? And there are schemes where actually going back to the very idea of non-equilibrium, that you switch on your system adiabatically and you follow the trajectories, and then you know which one to pick. But this is not how experiments are done. Sometimes you have a quench, sometimes you have a different way. And then sometimes you have a quench, and then the equilibrium, this non-equilibrium stationary solution evolves to something which is known. And that's, what is the solution that corresponds to this non-equilibrium stationary solution? And well, this is this question is not new. It starts in the 30s. There are many important advances, and there are many criticisms by guys that contributed to this community as well. And people use two apparently contradictory entropy production principles, maximum or minimum. And but there are some understanding why. And here we actually choose to use this approach here. And then the minimal toy model we employ is a toy model that actually is sufficiently complicated to have many minima, and is simple enough to be solved easily on a PC, which is a double quantum dot. I was speaking about a single one. The dots interact, the electrons interact, and I take an mean field approximation known as Hubbard mean field, and I compute the current, et cetera, et cetera. So the results are the following. So if I do the simple solution, I don't take, what is important here is that once I introduce this charge, there is a magnetization coming up. and a spontaneous magnetization. And so if I took the unpolarized solution, like most people do, I get wrong results. But if I take the polarized solution, then what happens is that most people doing electronic dynamics, molecular electronics, they look for the minimum of the energy. So I need 15 seconds more. And then you see that at different biases, there is a flip in spin projection. And the minimum would be the one with the minimum energy. However, if I use this minimal entropy production principle by Prigogine and others, then I see that there is no such flip except like here. And the question now is, so to what extent, well, there is a lot of debate here, and to what extent this matches into, let's say, including quantum information and other things. So these are the things we are thinking. Well, these are the things that are thinking these lines. And for the ones that want to discuss more about other things, we also have some work in pump systems, time-dependent Hamiltonians and the current generated by that in view of quantum information. Good, thank you very much. Sorry, I exceeded by 1.
So questions? So Gabriel?
Hi, Kai. Thanks for the very nice talk. Entropy production is related to dissipation. Where does this dissipation actually happen?
In the leads.
But not in the center. You're talking about strong coupling, so it's not really kind of in the strongly coupled regions, like far away, I guess.
Yeah. So this is, again, this is the non-trivial aspect of the Landauer-Büttiker construction, is that you have this transmission. Everything is related to, the current is related to transmission. But eventually, once you reach the reservoir, it doesn't come back. So all this is, it's an assumption that things relax in the reservoir. And surprisingly, it works. This is why it took so many years to establish this kind of phenomenological approach, but it really works. So just to add one thing, we can derive this with non-equilibrium Green's functions once we accept that we don't use that we take partitions very far. Okay.
So I have a question concerning the last part, so the expression linking the entropy production to heat and charge current can still be used also in the presence of interaction. Isn't it enough to compute it?
Yeah, the problem is, no, you're completely right. The problem is that so the problem is that we get conflicting results if you use different principles like maximal entropy, minimal entropy, and production. And there are different formulations, and we are sorting out. So experiments are very few because we use a very simple model. But you're right. I mean, given the formulas, we can compute the currents and the entropy production. Now we have the problem is to decide which one relates to a hypothetical experiment, and this construction is not in a very solid basis, to my opinion, right now. So this is the question that we're struggling with, and we would like to hear some input if somebody has something to say.
So I have a question regarding the TUR part. So, I mean, these TURs as originally kind of derived by Seifert and other people, like one of the reasons why people, find it so hard or you see such weak violations is the bounds are notoriously weak.
Yeah.
Now, I mean, so it would be desirable to have stronger bounds because then, like, one of the nice things of TURs is that they kind of bound any relative fluctuation of a current, so you can measure charge, current, bounded dissipation. So my question is, like, the other sort of thing that you derive in the mesoscopic framework, is that tighter in any way, or
no?
is this loose?
What we have is I'm sorry, if I wasn't clear. Yeah. So what we have is we have a lot of experience in evaluating these terms here for a generic system, and eventually this variance here is related to it's related actually to the conductance fluctuations and correlations, and this contains the quantum part or the quantum interference part of the process. And then for a number of systems, or depending on this parameter, we can actually reconstruct almost the whole curve. I mean, we can we have now an expression for establishing this, and for a number of systems, we know where is the inflection. And you're right, for all systems which are kind of reasonably modeled, I mean, in mesoscopic physics, that you have one or many resonances, the effect is exceedingly small, unfortunately.
I guess, like, I can totally understand, like, taking, one side of the equality and studying it, like, but why would you expect the bound to hold it all anyway, given that it was derived from classical math?
Yeah, this is fun because, look, yeah, this is a thing I asked myself as well. So we can show that for weak coupling, it is correct. And if you have sufficiently large gammas, it's an exact result for mesoscopic as well. So yeah, this, yeah. So this is an analytical result we were able to read. Yeah. Right.
One last question.
Thank you for the talk. Very interesting. I'm interested in many body effects in QTD. So, I have a simple question. I think it was partly answered, but let me ask again. So in equilibrium system, you have your minimization principle. In non-equilibrium system, you don't have it, but still you were looking for minima. At least this is what I understood. So I was confused by that.
No. It's, yeah, like.
You had some pictures and it looked like you were looking for some minima.
Yeah, sorry, it wasn't clear. So the thing is that, oops.
This one. Yes, exactly.
But let me flash this one before. So you derive the Hartree-Fock equations from a minimization principle. But even if you don't think about it, in several books, they actually skip this, and they basically, oh, look, if I do this, I end up with some self-consistent equation, and without even thinking about that this is what is behind, and the variational thing. And actually, this is the answer to your question. When you do Green's functions, you do the same. You don't resort to a minimization principle. You just stick in the Green's functions, do self-consistently, and then you find solutions when it converges. You are not looking for minima, you are looking for convergence. Depending on how you start, your initial guess, you end in different solutions, and then you ask yourself, okay, so what do I do with these solutions? Which one should I pick? So that's the point. In equilibrium, oh, I picked the one with the.
I understand now. Thank you.
And here.
Yeah.
And so the thing is that we're working with disordered systems, and then the solutions are abundant. And then the student was desperate. What is the? And I didn't know how to answer it. I think we still don't have a very good answer for that. This is the thing.
Okay, let's talk Kyle again. So for lunch options, I think we have three main options. You can go, there is a shopping mall there with some more expensive option. There is the cheapest one is just on the side here. We should go for this exit here. So if you turn right, you're just in the university, and there is just some places you can get a good and cheap meal there. So you can also go straight, walk straight ahead, and then you cross the main street, and there is some places which you have a food by kilogram. So it's a medium price thing. I think this is the three main options. No? So you can also ask us, the organizers, or anyone else here, and we can just go in groups also, I mean, at least now, okay? So there is no recommendations. I mean, so if you go to the shopping mall, there's gonna be many options in here also. Pode levar as mochilas aqui, você acha que tá? A chave da porta tá com quem? Yeah, we're not sure who's gonna have the key. Yeah.
and then which is the clicker. So that's forward, that's back. That's, ooh, very fancy. Okay.
Okay, so I think that we can start our afternoon session. The first speaker is going to be Steve Campbell, talking about thermometry in many-body quantum systems with impurity models. Okay,
Yeah,
the word's
cool.
yours. Thank you.
Okay, that is started. Cool. Yeah, thanks very much, and thanks obviously particularly to Tesa and the rest of the organizers for having me here. So my first time in Rio, it has been special. So what I'm going to tell you about today is a sort of series of works that I've been thinking about over the last couple of years, which kind of just falls nice, I think sort of fits nicely within the thrust of the conference. So on thermometry, right? So thermometry is, builds on ideas from quantum estimation theory. So it's very information theoretic, but then also we're doing something, we're trying to sense the temperature of something. And temperature I find is just an interesting quantity in quantum mechanics, because, as we even heard today, like what does it mean for like a qubit to have a temperature? It's not a very well-defined question. So, studying things like thermometry of quantum systems also opens up a whole lot of sort of foundational directions also to go. I'll not get into that too much. I really want to focus on today is just like how well can we sense something like the temperature of some system. And what I'll try and give you a flavor of and what I've learned over the last couple of years is that when you're dealing in particular with like many-body systems, studying things like the metrological protocols kind of comes in three flavors that I think is a little bit underappreciated. So very often we'll hear stuff to do with many-body systems being excellent sensors because of criticality. And so then we're leveraging the critical nature of the systems to be really good sensors. And that's true. That's the most normal way people, I think, look at critical sensors. But there are other flavors of critical metrology that you can do where, for instance, maybe you're sensing a critical system and then you've got like something like a single two-level, like a quantum probe or a few-body probe that you're putting in contact with something critical. Those two pictures are kind of complementary. But the motivation for where we started this was looking at the sort of third flavor that I think is very underexplored, which is imagine I'm sensing some system, some sample, maybe some many-body system, and I'm using some small quantum system like a single qubit. We're going to look at like impurities, 1 or 2 qubit systems. Neither of those two things on their own are critical, but then their mutual interaction induces criticality. Our rationale was in those instances, that's still a notion of critical metrology. Do you get some sort of advantage? Does the criticality give you some sort of better sensitivity? And we'll find that the results were, for me anyway, surprisingly subtle. So where I will start, though, is we'll go back and let's just do a quick crash course on how do we do sensing in general with a particular focus on thermometry. So as I've said, temperature I find is a really interesting quantity just generally to study in quantum systems. There's some foundational issues here, like, what does it mean to like take the temperature of a particular state? We're not going to get into any of the sort of more philosophical questions on it. We're really going to work from a kind of well-founded situation where I'm always going to assume there's some background ambient sort of classical temperature. That's essentially what I'm looking to estimate. I am going to consider actual sample systems, like particular many-body systems. But I'm going to assume that they have already reached some sort of thermal equilibrium with some background system. So there's always a sort of well-defined temperature that I'm interested in studying here. So that's my problem. If you're interested in some of these more philosophical side of things or the more general stuff, I'd recommend have a look at this topical review from a few years ago, which really covers the full breadth of basically what was known at the time in thermometry. But the basic tools, so I start from looking at I think what is the most common way to think about sensing and estimation theory in quantum systems, which is using the Fisher information. Right? If you're not familiar, Fisher information metric is basically just a distance metric. Right? So it tells you how different are two probability distributions. So if I have something, and it then makes sense why this is good for defining how good something is as a sensor. Because what do I do in a quantum system if I'm using it as a sensor? I prepare it, I do some measurements, I'll get some probability distribution. The idea then is, okay, imagine I then do the same system, they're the same setup, but I slightly tweak one parameter. I'll get a different probability distribution. If those probability distributions are very, very different, very far apart in their sort of in some relative space, then that probe is very sensitive to that small change. That's the rationale and that's what the Fisher information captures. So when we're dealing with, and the same basic idea with quantum systems, you then have the quantum Fisher information, which we don't need to get into the sort of nitty-gritty details. Just it's essentially the same quantity, the same idea, but just for density matrices or for quantum systems in general. Now, if I'm doing temperature estimation with quantum systems, super easy if I consider my whatever I'm using as my probe, whatever I'm using as my thermometer, if it's in thermal equilibrium. Because what it turns out then is I can calculate this quantity here. This is the Fisher information. And for a probe which is already in thermal equilibrium, I can calculate it, and what ends up being is there's only basically one contribution that comes from this, and it's related to the rate at which the populations of the state change with temperature. So you imagine I have something like a two-level system, right? Simplest thing I'm going to imagine here is just my two-level system. If it's, let's say I've put it in thermal equilibrium, and I'm just going to change the temperature a little bit. I want to know how sensitive the probe is to that small change in temperature. What this is basically saying is that the rate at which the Boltzmann weights basically change as a function of temperature fully dictates the sensitivity I can get. And it kind of makes a little bit of sense. What you'll find is if you ever calculate or you ever see any of these thermometry papers, any studies on it, you'll always have these kind of characteristic curves appearing like they're here, right? So it's a bit of a mess, this plot. But if we just look at just the solid curves, what you have there is essentially the Fisher information for a qubit, for a two-level system. What you'll always find is that there's some region, let's say we look at this delta where this is the gap, let's say it's just set equal to 1. There's some region where the Fisher information will be 0. That corresponds to a region where the temperature, which has some sort of effective energy scale, where the temperature is too small to get any excitations going into the excited state. So then in that region, you get no excitations, there's no rate of change in the populations, therefore you get no sensitivity. So what you need is always that the temperature you're sensing is sort of on the order of what the energy gap is, and then you'll see that what happens is when that happens, you get very quick rates of change, like lots of population starts flowing into the excited state. What's nice here is that it doesn't matter what the actual value of the population is, it's just the rate at which it's changing. So that's the important bit. It's just how, like basically the derivative of how that's changing is what dictates how sensitive it is. So if lots of populations
on the Hamiltonian of the interaction between the probe, let's say, and the system.
Yeah. Well, in principle, it would do. But here, what we're considering is just like sort of the probes are already in equilibrium. It's basically like weakly coupled to some sort of background environment, right? So if I just have a equilibrium probe here, I'm just looking essentially at the sensitivity to changing what the ambient temperature would be. So what you'll find in this instance, though, in all of these cases for a single qubit, is that there's always essentially a characteristic temperature that it's well engineered to sense, right? And it kind of makes sense again. There's one gap, therefore, when your temperature is on the order of what that gap is, it's kind of where the probe, this qubit, will act as a good temperature probe. And then when you ramp up to very, very high temperatures, you'll get progressively less and less excitations will start flowing into that upper state. It'll go to a maximally mixed state. You lose all sensitivity. So these sort of curves kind of make a lot of sense. I just mentioned that very often in this kind of approach where we use the Fisher information for characterizing the sensitivity or the precision with which we can determine something, we normally then look at the Cramer-Rao bound. So this is basically what tells us how accurately, so the variance in the parameter we're looking to estimate is inversely proportional to what this Fisher information is. So that's why we focus so much on the Fisher information very often here. I will try and convince you that that's not always the best way to look at it. There's a few subtleties that come in. Okay. Okay, I should speed up a little bit. So what we go way back, way back, I think like sort of 10 years ago, we think what makes a good equilibrium quantum thermometer? And this is a result, I think, from Gerardo and some collaborators back in 2015, where they used this fact, right? That, the Fisher information for an equilibrium probe is just the rate of change of the populations, right? So I know what I put my probe in a thermal state. It's the Boltzmann weights tell me what the populations are. The rate of change in the Boltzmann weights, summed in this way, tells me what the sensitivity is. And so then using this argument, it then becomes kind of clear that the best probe you can have will be something where you exploit some sort of high degeneracy. if I get, because what happens is if I have a ground state, a unique ground state, and then a highly degenerate excited state, the important part is the rate at which those states get excited, not the actual populations that go into it. So if I have like 10 states that are there, and they're all degenerate, they all start to get populated at the same rate, and then I basically get an n-fold increase in the sensitivity, because that's how the Fisher information enters in. So this essentially establishes what is a good characteristics for a probe to have. We were curious, and I think this was, I mentioned this just because it was my first introduction to thermometry where I got into it. We said, okay, well, can you, this highly degenerate probe has the same sort of constraints or the same limitations that the single 2-level probe would have, in that it's really good at sensing one temperature, right? So it's, again, because there's only a unique gap there. Can you play the same game in order to sort of get multiple peaks? So one of the first things we looked at was, what if I have like an anharmonic spectrum? If I have a gap here and then I have a different gap somewhere else, will I get sort of better sensitivity? What you find is that if you don't have high degeneracy, then basically all bets are off. Like that ground state gap is what dictates, it's what dominates everything. So we played the same game that the guys did in this paper, where we said, okay, how much degeneracy do you need in order to be able to resolve more temperatures? And so with Sebastian and Marco, we played about a little bit, and we took this idea and we said, okay, how much degeneracy would I need in some higher excited states in order to resolve temperatures, multiple temperatures, right? So I have different things. And what we found there was that you needed like inordinate amounts of degeneracy, right? So I just flashed this up to say, if I have a unique ground state and one unique excited state, if I want to get a comparable sensitivity at some other value, I would need sort of 2 orders of magnitude more states in the excited state. If I want to resolve like another temperature, I would need, again, something like 5 or 6-fold degeneracy. So not very practical. This was just us doing stuff out of interest. But what I want to go to is, so this is essentially what just got me interested in studying thermometry. We know, at least from, I think this really, it's beautiful PRL you should look at, what kind of characteristics a good equilibrium probe can have. So we want to see, well, what happens in this instance, or what general characteristics should a probe have if we look at a slightly more, I think, meaningful setting, right? Because what this is all doing is assuming ambient environment. So we assume that my probe is already in thermal equilibrium and that it's just sensing the sort of ambient temperature that's there. That's not generally, I think, what the question that we're most interested in. What we're really generally should be interested in is probing complex systems or probing actual samples. So here we're asking just a slight variation of a question, and this is where the motivation came in. What we were thinking was, okay, imagine instead of looking to estimate the ambient temperature, I actually want to know something like the temperature of a given sample. How does the specific details of the sample enter into how accurately I can determine something like its temperature? And our hope was that if we look at one of these situations where by coupling the probe to the sample, you induce criticality, then you would maybe get some sort of like, excellent super Heisenberg scaling or something. So in order to study that though, we had to take a step back and go, okay, well, what happens if I just do the most basic thing? I have like a 2-level system. I want to put it in contact. I want to use it as a probe for some many-body system, but there's no criticality or there's no nothing. I just want to know, how does the properties of this many-body system impact the sensitivity with which I can use a probe as something like a thermometer? So the setting that we considered was really like most basic setting we could imagine. We have some actual sample, which we normally model as like a fermionic lead, which has some spectral density, so it has some characteristics to it, but it's not critical, nothing like that. And we're going to drop an impurity into it. We're going to just couple an impurity to this guy with some coupling strength. And we're going to see how well can this guy act as a probe for the temperature of this many-body system. So like, as I said, we've already assumed that this many-body system has reached thermal equilibrium. There's some ambient temperature that we're looking to estimate. And we let the two of them talk to each other, thermalize, and then we're going to read off what happens with this guy. So this was really motivated just to give us a benchmark for the more interesting setting that we were looking to build up to. But as with many interesting problems. It turned out that just doing the benchmark calculations turned out to be surprisingly interesting. So we wrote a paper on it before we started doing the actual critical setting. So here, what happens in this instance, like essentially what we had to play with was the spectral features of the many-body system. So we're going to we looked at various different spectral densities and different characteristics of it, and then how the probe was coupled to it. What we'll find in this instance, and I'll just flash up one or two quick results, is that the nature of this the nature of the many-body system didn't have a huge role, right? It didn't matter if we took like a flat spectral density or some particular more complex, we looked at a whole bunch of different more complex versions. It didn't have a huge impact. It did change the features of the probe, but not massively. Because what ended up happening is no matter what way the probe was coupled to this fermionic lead, when we looked at the reduced state of the probe itself, this is just a two-level system, it was always diagonal, right? So it always looked kind of like an effective thermal state. The details of what populations it had, though, are kind of captured in this expectation of the SZ term, right? So this is the magnetization of this qubit, right? So it's just a diagonal state. The complexities of like the spectral density of this guy do enter non-trivially in here. So what the coupling to the probe does is that it maintains the fact that it's like just a two-level system. It has it in some effective, it's still at some temperature. And all it does is whatever the gap that we actually have here, right? This B field sets what the characteristic energy gap that my qubit has on its own. What the coupling with the rest of the bath does is it just tunes that. It just has some sort of effective tuning effect to it. So, but otherwise the characteristics are basically the same. What we see or what we end up finding is like what's much more relevant is how these guys are coupled to each other. If we couple them with something like an Ising interaction, you don't get any strong correlations built up between the probe and the sample. And in that instance, everything looks almost like the equilibrium probe that we started with, basically just a qubit sitting in an ambient thermal environment. So it works basically just as well. If we couple it with something more complex, something like an exchange interaction, that's where things get a little bit more non-trivial, and we'll see correlations built up, and that becomes very relevant when we try and do something like temperature sensing. So as just one small aside that I mention, and if you take nothing else away from this talk, maybe just this point, when you use the Fisher information as a metric for sensitivity, generally it's fine. In most instances, if you're measuring something like a phase or a field or something like that, then it doesn't matter if you calculate things with the Fisher information or if you use what we do here, which is the signal to noise ratio. Signal to noise is just basically taking into account like how big is my the actual signal, the actual number I'm trying to estimate compared to the variance that I get basically from the Fisher information. This becomes very important when we think about something like low temperature sensing, because what we're trying to do is estimate some very, very small number. When the number is very close to zero, you need a massive Fisher information for it to be properly meaningful. And that's often obscured in some of the studies that would look at something like sensing, particularly thermometry. If they just plot the raw Fisher information, you can get kind of false positives or false flags. You'll think you have this very large Fisher information, but actually if your temperature is effectively close to zero, you basically have very little sensitivity. So it's a little bit more subtle. So I just highlight that I think studying the signal to noise ratio is the much more relevant quantity to look at. So we did it for this problem. As I said, if I couple my impurity to my fermionic system through something like an Ising interaction, they don't build up any correlations, and then basically it looks just like the sort of free spin case. So I get decent sensitivity. There are details of the many-body system get imprinted on the details of this guy through the non-trivial interplay it has on this magnetization, but otherwise basically the same. If I look at the exchange interactions, things are a little bit more interesting, because what happens is my probe then becomes correlated with the sample. And this is something which, for quantum sensing, we really should be mindful of. If I'm trying to use quantum probes to sense some property of some other system, I have to put them in contact with each other. They have to talk to each other. So then I should really take into account what happens with for instance, the correlations there. So what we look at here, I do a very, very crass approximation here just to capture the essence of it, because the details when it's a full many-body system don't really change too much. So we take this narrow band limit, which is essentially just saying, well, my complex many-body system, I'm going to approximate it by pretty much one site, and it captures the essential physics. So as I said, basically things hold for the full many-body system here. But what happens now is if I have my probe coupled to this essentially like, narrow band limited sample, if they're coupled by an exchange interaction, my probe is still diagonal, so I can still calculate the Fisher information just by looking at the rate of change of basically of these populations as a function of temperature. And the observable ends up being just the magnetization. And then if I compare what happens with the entanglement, this probe then becomes strongly entangled in certain regions with the environment, with the sample. So in this sort of region, for some moderate values of the field, there's a bit of an interplay between how strongly coupled they are and what the applied field is and what the temperature is. In this low temperature regime, they become very entangled, and that corresponds to a signal to noise that's basically vanishing, right? So what this is basically telling you is that whenever I have strong entanglement established between my probe and the sample, I basically lose all metrological capabilities. It just loses all sensitivity. And there's a non-trivial interplay between how correlated my system, my probe is with the sample, and like the sort of precision that I can achieve. So what you actually find here is that in these instances, you really want like basically the probe to remain sort of uncoupled with the sample as much as possible. So this was, like I say, these were meant to be just preliminary results that ended up, I think, being a little bit more interesting than we had anticipated. So we looked at what happens for various different spectral densities and various other complexities, but basically this basic feature stands. When it comes to something like thermometry, building up correlations then pretty much scuppers you. You can't really do a huge amount. And it makes sense whenever you think about the fact that this probe, if it becomes entangled with the environment or with the sample, then the reduced state of it becomes highly mixed. And the more mixed it is, the less information it can essentially contain. But after doing this was then when we finally after about a year of working on that, then we finally came back to saying, okay, well, let's look at the original problem that we were interested in doing, which is what happens now in the instance where I have, let's say, some sample that I'm interested in estimating the temperature of. So it's in thermal equilibrium with some ambient temperature. And I then want to use impurities to estimate what that temperature is. And in this instance, we're going to consider a model where we have actual criticality that's induced. So I'm going to have two impurities, like a left impurity and a right impurity, that basically just drop in contact with my leads, right? And then in this instance, these are effectively just two qubits. They're coupled with some coupling strength, and I assume they have just an exchange interaction between them. And then they are respectively coupled to different parts of this environment, right, of this sample that I'm looking to estimate. What's nice or what's interesting in this problem now is this kind of falls into this strongly correlated electron problem that my collaborator, Andrew, would be an expert in, this sort of two-channel Kondo problem. So it's, in this instance, you have actual criticality that's induced. So notice, I have two qubits, so they're definitely not critical. I have essentially my two leads, which I can sort of think about as basically just one big lead I've split in two, that is also basically non-critical. It's a many-body system, it has some spectral density, but there's no critical feature there. But this coupling, the interplay between how strongly the two impurities want to talk to each other versus how strongly they want to speak to their respective leads, then leads to this frustration between them, and that leads to actual critical effects. And our hope or our expectation was, can I see some sort of enhanced sensitivity by leveraging that critical features? What we find is essentially, and to some degree, yes, a little bit. Really, when criticality emerges, again, you're basically scuppered again. Like what happens is that if really at the critical point, where what ends up happening in this instance is that the interplay between how strongly coupled these guys want to be with each other versus how strongly they each want to be with their respective leads, then leads to you basically form like a singlet state between these two guys and the rest of the bath. And then in that instance, that singlet state means that they're maximally entangled with the sample. And so when you look at the reduced state of them, you get no information. So you lose like the thermometric sensitivity in that instance, really at the criticality. But there's a non-trivial trade-off between them. So you can get a little bit of something out of it if you move a little bit away from the critical point. What I found more interesting was that if we look at the features of these two coupled probes when they're coupled in this very simple like exchange interaction way, they have the features exactly of what we need for like a good equilibrium thermometer, a good equilibrium probe. Because what you find is that this type of coupling naturally leads to some degeneracy in the spectrum of those two qubits. Depending on if they're antiferromagnetically or ferromagnetically coupled, you will either have degeneracy in the ground state or degeneracy in the excited state. So what you'll find in this instance is that if you have the right sort of coupling, you'll get good sensitivity exactly because you'll have something like a triple degeneracy in the excited state. So you'll get a threefold increase in how good sensor for temperature this guy will be compared to like just a single qubit. So there are ways in which you can squeeze a little bit out of it by making your probes a little bit more complex. But in the last sort of 15 minutes, what I shift to, which is maybe a little bit more on the information theory side of it, was an interesting observation that George kind of made whenever we were studying this. Because what we assume here is I've made my probe more complex. Right? I started looking at a single two-level system, so then there was one gap there, so I assume I know that guy. Here I've got two qubits. They have some coupling between them. What is clear in this instance, in order to have like good sensitivity, I want to be, let's say, in the positive K region, so I have a triple degeneracy there. So I need to know what K is. We ask a simple question like, well, what happens if I don't know K? Then we have to like slightly extend our formalism and we can go from using just the Fisher information where we're just estimating a single parameter, and then it elevates us to look at something like the multi-parameter estimation, where we say, okay, imagine I don't know all of this. In any of these estimation protocols, very often if I'm doing something like temperature estimation, I implicitly am assuming I know all other parameters of my problem with absolute certainty. That's not necessarily true, right? So, and in this instance, we're saying that the nature of my probe plays a highly non-trivial role in how useful it is as a temperature sensor. I want to be damn sure that I know what this K parameter is. So we ask the question immediately, well, what happens if I don't know K? Well, what does the multi-parameter Fisher or multi-parameter version of estimation theory tell me here? And this, I think, was really, I mean, I haven't seen it in the literature. I'm sure it is somewhere, but we kind of fleshed it out a little bit, and I found it very informative. So if we then take just the natural step and say, no, I'm not just estimating one parameter. I assume there's two parameters in the problem I want to know. How well can I estimate something like temperature, assuming I have some uncertainty in some other parameter, let's say this coupling, K, right? So I have two parameters that I'm saying there's some uncertainty in. The multi-parameter signal-to-noise ratio can be written in much the same way. It's basically telling you whatever the size of the parameters, the signal of, let's say, this could be my temperature, this could be my coupling. The magnitude of the product of those guys is divided by, and in the single parameter case, this was just the Fisher information. Now this has been elevated to a Fisher information matrix. And so what I have is I'm 1 over the inverse of the Fisher information matrix. That leads to a subtlety, right? Because I can still write down what my Fisher information matrix is, and then I can invert that matrix. What the matrix looks like is I have terms on the diagonal that are basically this single parameter Fisher information. This would be how accurately can I measure, say, the coupling K. This is how accurately can I measure the temperature T, right? This is just the Fisher informations for the single parameters. And then on the off diagonals, I have the correlations, the relationships between them. Because this is a matrix, then this term can sometimes, this inverse is sometimes not defined. So you can have a singular matrix here, and then if this is singular, then this multi-parameter version of the Cramer-Arrow bound is meaningless. If I have a singular matrix, then I can't invert it, then it's just, I have no meaningful way of talking about the sensitivity in this instance. I think Matteo Paris has a beautiful way of describing this. He says that whenever we're studying things like the inverse of this, and whenever it's singular, he calls it a sloppy problem or a sloppy parameter estimation problem. But in the instance where it's not singular, pushing this a little bit further, we get some very nice insight as well from this multi-parameter picture, because we can ask, well, what the multi-parameter guy is telling me is for some parameter, let's say this is my temperature, how well can I determine the temperature, assuming I have some uncertainty in some other parameter, which here for us is something like the coupling. And when you work out what this term is using these relationships, what you'll find is that it's bounded always by what the single parameter estimation is. So how accurately can I determine my temperature, assuming all other Hamiltonian, all other problem parameters are known with absolute certainty, minus a term which is basically related to the correlations between the two. And again, this is a strictly positive term. And so what you'll find is that you're upper bounded always by the single parameter case, which intuitively makes sense. And then you always lose. The more uncertainty you have in the other parameter, you lose a little bit here, right? So the better I know the other parameter, the better I can estimate the other, whatever parameter I'm interested in. When it's singular, this thing basically just blows up and it becomes like poorly defined. And if we go back to our problem, to our two impurities dropped inside our many-body sample, what we find is that in that instance, if I say, okay, imagine I want to estimate temperature, but I don't know the K, I calculate the Fisher information matrix, and I try and invert it, it's always singular, which basically is saying that in this instance, I can never estimate temperature unless I know with absolute certainty what the coupling is between the two of them. And that seems like a catastrophic situation for parameter estimation, basically saying that for a fairly straightforward, fairly simple problem, that if I don't know with absolute certainty all of the relevant parameters, then all bets are basically off. So we asked, okay, is there a way in which we can lift the singularity in the Fisher information matrix? Is there something that we can do? And it turned out that for this problem, there was something a little bit, right? So we said, okay, what we can try is introducing a little bit of additional control. So we kind of complicate the problem a little bit, but what we say is, okay, imagine that for my probe system, I add an additional field to them, right? And what that field does is it breaks the degeneracy. So if I compare here, this is what I would have if I have no field applied. This is the previous case where the excited state would be degenerate or the ground state would be degenerate here. You see exactly what we would expect from the first couple of slides I told you, that when the excited state is degenerate, you get a sensitivity that's kind of like 3 times bigger than what you get whenever the ground state was degenerate. So this is exactly what we kind of expect. If I add this little symmetry, or this little this field, in this instance, the Fisher information matrix is singular. So in principle, unless I know absolutely certainty what my coupling is, I cannot do any sensitivity. I can't determine what the temperature actually is. If I add this breaking field, what ends up happening is I get the single parameter estimation, the single parameter signal to noise looks like this. So it changes the quality of the features a little bit. So I still have good sensitivity in 2 different regions. I actually get a bit of an enhancement here for details that I'll not go into. But if I now look at the multi-parameter case, the Fisher information matrix is no longer singular. So I can actually do proper multi-parameter sensing. There's no kind of catastrophic failure here. But the region in which I get the best sensitivity is kind of significantly changed. It's actually whenever I have the ground state quasi-degenerate is kind of where it's more sensitive. I don't have time to sort of go through the particular details as to why that's the case. I think the main takeaway I want from here is that whenever I'm doing a parameter estimation problem, I implicitly assume that I know all other Hamiltonian parameters, but that's not really the case. If I consider the multi-parameter Fisher information, it will tell me that I'm completely screwed, basically, that I cannot do any sensitivity. But what I can do is I can add some control to it. So here I just add a simple field, and that is enough to break that, to lift that singularity and recover some notion of sensitivity. What I liked a lot about this, and then the last 5 minutes I mentioned, is that my student George, who was doing basically all of the work on this, was then sort of interested in pushing this a little bit further. because this Fisher information matrix approach is kind of a bit of the worst case scenario. Because what this is assuming is that I'm looking to estimate the temperature and I do not know the coupling at all. It's assuming I have no information about the coupling term, which is, again, maybe not the most realistic setting. In reality, if I'm preparing my probe, it's reasonable for me to assume that I can prepare it with some certainty. Maybe I don't know precisely what value the coupling I'm using, but I know roughly what it is. In that case, we can take a different approach to defining the multi-parameter picture, or a different approach to asking, well, what happens if I have other uncertainties in my system? And that's what we've done in this most recent work, which is just, we say, well, if I imagine I'm preparing my system, my probe, and there's some relevant parameter that I have control over, which in the impurity case was the coupling. So let's assume I roughly know what that is, but I don't know precisely. In this instance, then, what I can do is assume I have some sort of reasonable distribution of values that can be, where the mean is kind of centered on what I think I'm using, but there's some sort of classical, essentially, uncertainty around it. So that's what we're doing here. I change parameters because we look at a different model here. But essentially, it's assuming that this is the parameter, like the coupling, let's say, that I have control over. I assume it has some average value, but then my actual state, I then construct as a distribution. So here we use a Gaussian for convenience, a distribution over all of the other different possible values that I could take. And what we're interested in doing is then estimating what this omega parameter is. So what this then does is, instead of all the previous cases where we basically were just calculating the Fisher information of like one state, we now calculate the Fisher information of this object, of this density matrix. So where we have some average value that we think we're using, but then there's some classical uncertainty sort of spread around it. What we looked at here was one of those other flavors of critical metrologies that I mentioned at the start, where we're saying, okay, imagine that my probe itself is some sort of critical system. So we look at an easing model here. So we're assuming we know this J. We're going to take everyone to be coupled in the same way. And we assume it takes some average value, and there's some distribution that it's spread around. And we're looking to estimate what this omega is. If we know G, this coupling term with absolute certainty, what we get here is the red dashed lines, right? Where if we focus here on the G equal to roughly 1, this is basically where the easing model is critical, and you get kind of the sharpest sensitivity. So the Fisher information here is what we're looking at, and it kind of takes its largest value. If I introduce some uncertainty, then what happens to this peak is that it starts to drop and to sort of spread out. Again, this sort of makes sense. If I add some uncertainty, I don't lose all possible information as soon as I'm not absolutely precisely certain of what the coupling is. It just sort of smears out my knowledge. So it starts to drop off a little bit. Until you get to really very, very basically where your Gaussian is like completely flat, and then you'll lose all possible sensitivity. But what was very cool was this plot that George generated. So if we look at these many body probes, like this, like an easing model, the critical sensitivity, like in this region, around about where the critical point would be, then that's where we predict to get like this sort of super Heisenberg scaling, like this really, really sensitive parameter estimation. And you generally find that the sensitivity, the Fisher information scales kind of quadratically with the size of the system. That's what this this green line is saying, that we're getting like a n squared scaling of the Fisher information. That's the best that you can do with these models. While what classically you could do with just uncoupled systems would be this lower bound, this red line. That's just where you have like linear in the size of the system. What we have here in the dots is basically what happens whenever we have different increasing values of the uncertainty of this Gaussian distribution. If the distribution is really small, where it's basically 0, we keep this n squared scaling, right? These black points are basically saying I still have absolute best sensitivity I can have because I basically have no uncertainty. If I open up the uncertainty a little bit, if I look at one of these other curves, what's interesting is I find that it can tolerate a certain amount of uncertainty. There's a bit of a trade-off, like a given size of system can still recover the n squared scaling up to a point. And then at some level, then it starts to drop off. So there's an interesting trade-off between how accurately I know basically my control knobs in how I'm preparing my probe and how accurately it can act as a good sensor. So this kind of main conclusion was it allows us to, well, sort of be confident that critical probes are actually still quite useful. Like even if there's a bit of uncertainty in how precisely I've prepared the state I'm interested in, I can still tolerate a certain amount of it, provided the system's not too big. But then it also, highlights this point that actually the best quantum probes are not going to be like really like in the thermodynamic limit, because then they will not be able to handle any uncertainty in the other parameters. There's going to be a bit of a trade-off. Sort of these mesoscopic size systems are probably going to be the best ones. I have 5 seconds to finish, so I will skip over this point just to say that thermometry is a massive field. I didn't talk about these other things like dephasing style protocols or collision models that you can do. But I'm happy to discuss at length this week about it. And the last 2 things I will say is I'm organizing a conference in Dresden in July that is tangentially related, I think, to here. It'll be mostly focused on quantum control. So if you're interested, yeah, take a photo or just chat to me. It'll open for submissions at some point in around about January or February. We have some very nice speakers lined up. So, and the last bit is to say I'm also guest editing a focus issue with Irene and Mario about thermodynamics in quantum platforms. So this is a quantum thermodynamics conference. I invite you all to submit, please. Whatever you have, feel free to chat to us. Deadline for submissions is we're gonna push it out probably until February or so. So if you have something you feel would fit within the scope of the issue, please feel free to chat to us. And so with that, I am 50 seconds over. So thank you very much for your attention.
Thank you, Steve. So we have time for questions. Perhaps one here first.
Hi, Steve. Thanks for the talk and very nice one. I'm wondering, related to this results of the 2 probes. So the question is this insensitivity, is this singularity related to symmetries in the system? First question. And second, if it is the case, how sensitive it is to this symmetry, in the sense that if I break this symmetry just a tiny bit, then I get rid of the problem? And how is it related to your approach?
So, excellent question. And my basic answer is I don't know yet. So what we're doing in a follow-up work at the minute is we're looking at exactly like a XY chain. And we're saying, well, what we find there is that if the system is too small, if it's like 3 qubits, and you're doing something like estimating temperature and field or field and coupling or something, if for any of those 2 parameters, the Fisher information matrix is always singular. But if you go to a slightly larger system for 4 qubits and above, there's no singularity in the Fisher information matrix for 2 parameters. It becomes dependent on how you parameterize your Hamiltonian. There's a lot of subtleties. What we think is going from 3 qubits, let's say 3 qubits with nearest neighbor is basically an all-to-all connected model, and going to 4 qubits, then you have some notion of kind of geometry kind of there. There's some non-trivial distances that enter in. And I think there is a symmetry that's broken there, but I'm not entirely sure. So.
Sure, but then if you assume that each one of them are slightly different from each other, like you break this symmetry in that sense.
That, I don't know. I think maybe you lift the same singularity, but I can get my student to check. No. Yeah. I don't do calculations anymore, unfortunately.
So in the single parameter case, you want to minimize the variance of the temperature. In the multi-parameter case, the sum of the variances, or?
So there's a really non-trivial interplay between them. So what you find is in the single parameter, you can always find there's some, like the Fisher information is maximized by some observable. Whether or not that's implementable is neither here nor there. There is one that exists. In the multi-parameter case, you basically don't have, except for very unique situations, you don't have observables that simultaneously will give you the maximum Fisher information matrix or maximum Fisher information for your 2 parameters. So there's always a kind of non-trivial trade-off. You're never exactly being able to estimate both with the best precision, which is what we showed in that in this relationship here. This term, this is the kind of codependence, the covariance between the two. And that's essentially what ends up, and it's a really non-trivial problem, I think.
And what is the difference with metrology in general? Is it just a specific case, or there is?
I have been, well, I wouldn't say attacked, but I have been criticized before for saying this is how metrology works, because this is only one approach, right? Like where we use, I think it's called like, the frequentist approach, where you use something like the Fisher information matrix. What we're doing at the minute is also thinking about what happens with like Bayesian approaches. And then this whole like Pomerleau bound and stuff doesn't really apply in that instance. You have a very different kind of picture for parameter estimation. So I think it's some subtleties.
Okay, we have time for 1 or 2 fast questions.
So Steve, in the case you have just one probe, so perhaps a naive question, why not using common response functions like the susceptibility to see what is the temperature? Because if it's non-critical, we know how the magnetic susceptibility behaves with temperature. If there is criticality and you know the symmetry class, you know how it diverges. And
so I think in this instance, in the single parameter case, I think you're right. It's essentially the same though. I think the Fisher information is like if you expand out the susceptibility, the first term in that expansion is the Fisher information. So I think they are basically the same thing. What's nice though is then when you go to this multi-parameter case, then I don't think you have a complementary version of like a multi-parameter susceptibility. Maybe you do. Condensed matter theorists will correct me. So that's maybe one of the reasons why I like this framework more, but you're absolutely right. You could just calculate the susceptibility and it would tell you the same, I think.
Okay, so.
Thank you for your great talks. And as I'm working on the quantum critical methodology, I met the problem about the critical slowdowns, which means that we can get a large quantum Fisher information, but we need a large time to encode the parameters. So because my model is different from yours, but don't you have that kind of problem or not?
So I actively avoided that problem. So what we have here was we just assumed we could prepare the states close to the critical point, and we make no sort of assumptions on how you do it, because you're absolutely right. There's, again, lots of subtleties in how close you are to the critical point. I think there's a really interesting line to study where you think about what is the trade-off between how quickly can I prepare a state getting close to the critical point, but not necessarily there where critical slowing down scuppers you, versus how much benefit you can get. And there's some non-trivial trade-offs that I think, definitely we should look at.
Okay, so I think that we can leave the rest of the questions for the coffee break session.
Yeah, sounds good.
Yeah, and thank you, Steve, again.
Thanks, guys.
Okay, that's good.
Okay, so the next speaker is Hannah. Is going to talk about critical assessment of information flow in measurement-free teleportation. Okay, the word is yours.
Yes, thank you very much. And thank you so much to the organizers for all of the work that you've put into this really brilliant conference. It's so lovely to be here and to be able to share my work with you. The motivation really behind this project, the overarching aim, I guess, that this fits into is studying the resources needed for quantum information processing tasks. And specifically, we're looking at quantum teleportation, which is obviously really key in quantum communication protocols, but also in quantum computing, especially distributed quantum computing. And it's long been accepted that entanglement is the essential resource behind teleportation. However, recently, there have been some doubts around that. So there was a paper that was put on the archive a couple of years ago saying that there could well be a link between non-Markovianity and measurement-free teleportation, which I'll explain in a second. So basically what this project does is just really take a deep dive into that claim and study some measures of non-Markovianity and really try and get to the bottom of what are the resources here. Is non-Markovianity key for teleportation? So just a quick outline. First of all, I'm going to go over the background, explain what this measurement-free teleportation is, why we use it, and then look into the claims that were made a couple of years ago. And then I'm going to go over 3 different kind of definitions and quantifiers of non-Markovianity that we study. And we look at 2 different approaches as well of modeling the dynamics. And then if I get time at the end, I'll very briefly cover the study of the system environment correlations as well. So yeah, normally we think about teleportation in terms of communication over long distances. So Alice and Bob share a Bell state. They're located usually very far apart. Alice has a quantum state that she wants to teleport to Bob. She can perform a Bell state measurement on her 2 qubits, relay the information to Bob about the outcome that she gets. And then Bob can do the appropriate transformation on his qubit, and he can end up with exactly the qubit that Alice had on her side that she wanted to send. But we don't actually need to use measurements for this. This can all be done using unitary operations. And this was designed originally for more of a quantum computing framework where your systems would be close enough together that you could perform these unitary operations. However, it's also really useful for studying the dynamics within teleportation, because whenever you take out the measurements in the classical communication, it just makes it a lot easier to study in that way. So first of all, what happens in the original measurement-free teleportation circuit, so also called the BBC circuit because it was proposed by Brassard, Brownstein, and Cleve back in 1998, so a long time ago. So we have this qubit in system A. There we go. Whoop. There it is. And it's just in a generic quantum state. So the first thing that we do is we make our resource state. So the 2 systems in B and C, we entangle those to make a maximally entangled Bell state. And then the next thing that we do is we form this C0 and Hadamard on systems A and B. And that means that the information about our unknown state psi is now transferred into the correlations between A and BC. And then the next step is to perform similar operation on B and C, and that uncouples B from this so that the correlations between A and C are what now holds that information. And then finally, we do the same thing between A and C, and that means that all of the information is fully localized in system C. So this is the measurement-free teleportation circuit. So what this new paper, so this was by a group, they were at that stage in Harvard University, now they're kind of all spread out a bit more. But they kind of considered teleportation as a quantum channel. So they modified this BBC circuit and the protocol to reframe it in terms of a system and environment. So your system is kind of system A, and then the other 2, your resource, is labeled as an environment. And then instead of just using a Bell state as the resource, they varied the correlation so that they could study what happens whenever you don't have that maximal entanglement. So in detail then, how did they modify it? So first of all, this first system A, as I called it before, is now just our system. And then these other 2 are environment 1, environment 2. So first of all, we now have E1 and E2 in a Werner state. So this is just a mixture of Bell state, phi plus, and just a maximally mixed state. So the correlations in this state look like this. So we have both quantum and classical correlations as long as P is greater than 0. So the quantum correlations here are characterized by the quantum discord. However, you don't have entanglement unless P is greater than 1/3. So that's kind of what's going on in this Bell state as we vary the parameter P. And then what we do is we introduce these swap gates here, because what we want is to really study the system, the effect of the dynamics on the system. So what we want to do, instead of sending the unknown state from system A to system C, we wanted kind of to go into the environment and then see if it can come back out again. Can we totally recover it at the end? So we add in these swap gates so that the unknown system should hopefully, in an ideal case, be totally relocalized again in system S. So that's the approach that they take. So this is a plot from their paper. So we have here just the initial fidelity. So obviously you have a fidelity of 1 with the initial state before you perform any interactions or any operations. And then it drops to 0.5. So the system state, so the state at this point of the circuit has a fidelity of 0.5 with the original initial state. And then at the very end of the circuit is this blue line, and this is where it changes. And it depends on the Werner state parameter P. So we do recover the information that was in the state originally. As long as P is greater than 0, we should recover some of that information. And the argument is that because there's information flowing back into the system from the environment, that there is some non-Markovianity. So in Markovian dynamics, these are the dynamics that we can model using our standard Lindblad-Master equation. And information about the system will only flow out into the environment if it's Markovian. So if we see any information flowing back in, that must mean that there's some non-Markovianity here. That's the argument that they make. So what we did then was to quantify the non-Markovianity, study it in more detail. And then since we have this entanglement in the resource and we see that the correlations in that resource state are rising with P, and the information backflow is also rising with P, we also had a look at the relation between the non-Markovianity and the correlations in the original resource state. So how do we model the dynamics then? So this is our circuit. So we just took what I'm going to call the standard approach, where we take all of the gates, multiply them all together, and then we have this Hamiltonian here. So we just take minus I log and the multiplication of all of these unitary gates. So then the system at time t is just the initial state having evolved through the system, and then we trace out the environment. So I'm going to look at 3 different measures of non-Markovianity. So non-Markovianity is not really a straightforward thing to define and to quantify. There's many different definitions, so I'll go through the 3 that we looked at. This first one, this BLP one, is about the trace distance. So trace distance is a way of measuring the distinguishability of 2 quantum states. And the trace distance has this property that if you have 2 different initial states and they're undergoing the same dynamics, then they will get closer together. They will tend towards the same steady state. So what that means is that the trace distance between these 2 initial states will get smaller and smaller necessarily if you have Markovian dynamics. Therefore, if we see an increase in 2 different initial states that are undergoing the same dynamics, then necessarily we will have non-Markovianity. And we can use this to quantify non-Markovianity by looking at the rate of change of this trace distance. So we integrate over all of the areas where the trace distance is increasing, the rate of change is positive. And then we maximize that over all the possible initial states that we start off with. So that's the first one, that's BLP. Then secondly, we looked at LFS. And this is a very similar idea, only this is based on the quantum mutual information, which is given here. So this is the von Neumann entropy of the system S, and then the von Neumann entropy of an ancilla that it is coupled to. And then you take away the von Neumann entropy of the whole system and ancilla. And it's a very similar thing. So if you have a system and an ancilla that are coupled at the beginning, and then the system undergoes certain dynamics, then if you have Markovian dynamics, you will only lose those correlations between the system and ancilla. So the quantum mutual information characterizes the total correlations between system and ancilla. So then again, if you see any increase in those correlations, that must necessarily mean we have non-Markovianity. And very similar idea again with how to use that to measure non-Markovianity. You look at the rate of change again of the quantum mutual information, and then you integrate over all of the areas where the rate of change is positive. And we start off as well with a maximally entangled Bell state of the system and ancilla. So one important thing to note about both BLP and LFS measures are they are sufficient but not necessary conditions for non-Markovianity. So what that means is if you see an increase in trace distance, then you definitely have non-Markovianity. If you don't see it, then you don't know. You might still have non-Markovianity and it just doesn't show up in that way. So then the third method that I'm going to go over is the RHP one, and this is necessary and sufficient, and this looks at the divisibility of the dynamics. So if we have a completely positive trace preserving map, and we want to divide the time into these small intervals, so between a time t and t plus epsilon, then how we can find this is by basically starting off at time t, going back in time, applying the inverse map to go back to time t equals 0, and then going forward again to t plus epsilon. And here's where potential problems can come in, because this inverse map might no longer be completely positive. So if this whole map with the inverse is completely positive, then we call it CP divisible, and the dynamics are Markovian. Otherwise, they are definitely non-Markovian if we don't have this CP divisibility. So this is a bit more tricky to measure, but basically you use this function f. So you take a system and ancilla again, have them in a maximally entangled Bell state, and then you find the trace norm of this state after the system has gone through this short time interval of the dynamics, so from t to t plus epsilon. F is equal to 1 if and only if the dynamics are Markovian, otherwise f will be greater than 1. And then we sort of translate this into this function g, where g is f minus 1 over epsilon, and this will be either 0 if the dynamics are Markovian or greater than 0 if not, and then you integrate over that from t being 0 to infinity. Okay, so whenever we actually apply that then to the dynamics of our system, this is what we get. So the first one to give a positive value for non-Markovianity is the RHP measure, which is what you would expect because it's the necessary and sufficient condition. So we get non-zero non-Markovianity for p greater than or equal to 0.41. And then next we have non-zero BLP measure for p greater than or equal to 0.5. And then finally, we also see this increase in the quantum mutual information for p greater than 0.65. So for all three measures, we do see non-Markovianity in the dynamics at a certain point. However, whenever we look at the actual values that we're getting, it's kind of not very convincing because these are quite low values. So for some of them, it's quite hard to quantify because RHP could technically be infinite. But for the BLP measure, it has an upper limit of 1. So we're seeing that even if we have this perfect entangled state for p is equal to 1, we're still getting a BLP of like 0.08. So it's not really suggesting that there's a ton of non-Markovianity here. Another thing to note is that we only see non-Markovianity whenever the Werner state is entangled. So p is always greater than a third whenever this non-Markovianity shows up. But then this kind of begs the question of, well, why did Spiros and the guys in Harvard see, you know, such good information backflow, even whenever p didn't have it, p was small enough so that the Werner state didn't have any entanglement at all? Where's that coming from if we're not seeing it in how we've modeled the dynamics so far? So what we did is we took a new approach to modeling the dynamics, and we kind of split the circuit up into these individual gates. So instead of one big Hamiltonian that covered the entire circuit, we take 8 separate Hamiltonians that cover just one gate each. So then whenever we look at the system at time t, so we have our initial state, and then whichever gates are applied up until this point, and then maybe if we are wanting to study the dynamics at this time here, during G5, then this is the one that has the t applied to it at either end, and then trace out the environment. So this is the new kind of alternative approach to the dynamics that we take. And then in this case, we actually don't really need to even go into all of our measures of non-Markovianity, because we look at BLP and automatically we are getting entanglement straight away. Even whenever P is equal to 0, which is very confusing, because then the Werner state is just maximally mixed. It's just, there are no correlations in that state whatsoever. So it's hard to know exactly what's going on here at this point. But if we look at the values of non-Markovianity that we're getting, they're much, much higher. So already, it's very clear that there is good levels of non-Markovianity here. And we're kind of getting what lines up more with Spiros-Circus's results. And we're getting a non-Markovianity of 1 whenever the Werner state is maximally mixed, which is kind of makes more sense concerning what they said. So this begs the question of, well, why on earth would we get such good levels of non-Markovianity then whenever P is equal to 0? So we investigated that a little bit. We looked at the trace distance to see when does this trace distance actually grow? When do we get this positive rate of change? So we find that the optimal initial states to take are simply just the computational basis states. And then we look at the trace distance as these states evolve according to these dynamics. And now our time goes from 0 to 8 because we're using these like 8 different Hamiltonians. They all evolve, kind of for 1 unit of time each. So basically what we find is that the non-Markovianity, it only appears in this last, very, very last gate of the circuit, which is, if you remember, a final just swap gate. So then it seems very artificial, because if the non-Markovianity is just coming from a swap gate, this last swap gate was not actually part of the original protocol. This was the modified one that we changed because we wanted to study the dynamics in terms of system and environment. So is this just, a very shallow result? Is that all that this is? So if we look at the original BBC protocol and look at the environmental qubit 2, which is the one which was our qubit C that the state would have been sent to in the original protocol, do we still see this increase in trace distance? And the answer is yes, mostly we do. The only time that we don't see it is whenever P is equal to 0. As you can see, there's just this flat line of no growth in the trace distance whatsoever. But for all of the other values, then we do. As long as P is greater than 0 at all, then we do see this increase in trace distance, which again matches the plot from the previous paper by the Harvard group. So the final swap gate just adds this kind of superficial result for P is equal to 0, but otherwise there is genuinely non-Markovianity in the dynamics, even in the original circuit. Okay. So just to summarize these first results before I just quickly touch on the system environment correlations. This connection between non-Markovianity and the performance of a teleportation protocol is very, very highly dependent on how we actually implement this circuit. So it's not enough to kind of just look at the protocol on its own and study that. You have to really think through how will the dynamics work whenever we actually carry out this protocol in whatever physical or experimental setting that we're looking at. Because clearly the results that we're getting are very, very different depending on how we actually approach these dynamics. So yes, and then just to remind everybody, so in the standard approach, we see small amounts of non-Markovianity whenever P is greater than or equal to 0.41. And then otherwise, in the gate-by-gate approach, we see high levels of non-Markovianity whenever P is greater than 0. So very briefly then, the system environment correlations. I'm just going to talk about entanglement here. We also looked at discord and classical correlations. So I'll kind of give you a bit of a summary of that at the end. But we just looked at the logarithmic negativity to measure entanglement. So taking the standard approach to the dynamics, this is what we get. So we see that we have kind of entanglement of 0.5, which is the highest in the plot whenever we have the highest amount of non-Markovianity. So whenever P is equal to 1, which is what we would expect. So yeah, so far we are seeing a relation between entanglement and non-Markovianity, which was as predicted. However, I'm still not totally sure why this is. We get this small raise of entanglement also whenever P is equal to 0. So I haven't got to the bottom of that yet, but this is quite a curious effect as well that I need to look into. So it's not a completely straightforward result, but we still do see the overall trend that we expected. And then taking the alternative approach to the dynamics, we see the same thing. We see greater entanglement coming between the system and environment correlations whenever we have the highest amount of non-Markovianity. However, studying this in more detail, whenever we change the initial state, so the state that Alice wants to teleport, whenever we change that for the standard approach to the dynamics, it didn't really have that much of an effect. It changed the graph very slightly, but you still see exactly the same patterns. Whereas in the alternative approach to the dynamics, the graph completely changes. So we have, whenever we take the initial state just to be the computational state 0 in this plot, and then we change it to plus, so the superposition of 0 and 1. And then we find a very, very different plot, but still with the same pattern that you get more entanglement with more non-Markovianity. So we did also look at the same thing for Discord, because we were wondering, well, maybe because we get non-Markovianity growing for P is greater than 0, not just P greater than 1/3 whenever the entanglement appears, maybe Discord is also contributing to the non-Markovianity, but that's not true. We don't see any relation. There's no, you don't get any kind of clear patterns like this. It just changes depending on the graph, especially in these two. And then otherwise we don't see. It's actually greater whenever P is equal to 0. The classical correlations, it's similar. We don't see any relation apart from at the very, very end. We find that the classical correlations, that is where if we don't get Alice's state completely transformed back to the system, then where it lives, that information that we're losing is in the classical correlations between S and E1, E2. So during most of the dynamics, the classical correlations don't have much of a relation, but right at the end, they do give us some information about where the information has gone if we don't have it in our system at the very end of the protocol. So yes, we can see that entanglement and non-Markovianity are indeed related. And yeah, the dynamics are mostly non-Markovian whenever entanglement is highest. So in conclusion then, yeah, we have very weak evidence that non-Markovianity plays a key role in measurement-free teleportation. And we have to remember to take into account the actual way that the protocol is implemented and not just the protocol itself whenever you want to determine the resources that are needed. And yeah, our work stresses the need for this continued search for a resource theory of non-Markovianity. So thank you all very much for your attention.
Thank you, Hannah. Questions?
I'm always confused about the concept of resource theory of non-Markovianity, because it's like everything that is like a huge thing, right?
Yeah,
Can be anything. It's like saying the geometry of non-circles. It's like every other shape you can have. Do you have any, I don't know, idea to how we can approach this? Is there like one resource we can consider? Sorry, it's a tough question. If you don't know.
I mean, yeah, no, it's yeah. I've really copped out at the end of this and being like, this is somebody else's problem.
I guess if you knew, you would have written the article.
Yeah. But yeah, no, it's true. I think I think it would. I guess I'm coming very much from a quantum information perspective, but definitely more in the information part of this conference than the thermodynamics part of this conference. So I guess, in my mind, what I would start off with, considering my background, is to look at various tasks, I guess, within quantum information and seeing where does non-Markovianity actually play a role, where is it actually important. But I mean, that would be the absolute tip of the iceberg. So yeah, I'll need to think about that a bit more. Yeah, but it's a great question.
Thanks and sorry for the question.
No. That's yeah.
And Hannah,
Yes.
thank you for your talk. It was very nice, and thank you for filling the gaps, because now I fully understand this archive paper, because
Yes.
since then it appeared, it was a mystery for me.
Yes. Okay.
But something interesting in your paper is that you need to consider that your environments are in a Werner state.
Yes.
You don't discuss how you construct this Werner state. For example, you don't need to construct how you start with, for example, the zero state, and then you have some protocol to get to this Werner state.
Yeah.
Well, did you try any other entangled states for the environment, or even separable states, and trying to see if your construction of a measurement-free teleportation protocol will give you some connection between entanglement and other correlations, for example, coherence or discord or classical correlations or something like this? Did you try something like that?
No, we didn't try, but it's a great point, because maybe there's some intricacy about the actual structure of the state as opposed to just the correlations that are in the state. So yeah, no, that's a good suggestion. And then one thing to add as well is that I guess if you wanted to create a Werner state, it would just be depolarizing noise. So that would, it would hopefully be easy enough to create, but other states would be good to study.
In the case for P equal to 0, you
Yes.
have a maximally mixed state for the environment.
Yep.
And if you remove the last swap, it sounds like a DKC1 type of problem. You notice the DKC1 where you estimate the state on the end of this.
Okay.
It's
Okay.
something like
Yes.
this. It sounds like this. And in this scenario, the correlations play lots of important roles.
Okay.
And then including this classical simulability of the states. So maybe we have to.
Yes, that would be
I have a
great
bunch
to
of
discuss.
questions about this.
Yes.
Thank you
No,
very much.
definitely. Yeah, that would be great to discuss. Thank you. Yeah.
Thank you for this very nice talk. I have to admit, I'm very, very confused now. But so I'm not sure if it's a fair question, but I want to ask you about the part that you didn't really talk about in your talk, and that was quantum discord and classical correlations.
Yes.
So you did show that the measure of non-Markovianity based on the mutual information is consistent with everything else. But discord is just part of the mutual information, and the classical correlations is the other part.
Yes.
And you said that there's no signature of non-Markovianity in the classical correlations as well as in discord. So where is it?
I guess, well, so I guess one thing is that the non-Markovianity doesn't appear unless, for the LFS measure, it doesn't appear unless the resource state is entangled. So I don't know if it does need that as a prerequisite for that to show up, because I guess within the world of correlations, I mean, quantum discord, maybe it's that you need a certain amount of quantum discord, which also, looks like an entanglement. But yeah, it's something I need to think about. Yeah.
Thank you.
Yeah, thank you.
Okay, so let's thank Hannah again.
Yeah.
Isso aqui só para ele.
Isso. Direito para a esquerda.
Eu ponho.
Só segurar o do meio.
Ah, okay.
Okay, so then we can go for the last speaker of the session, Diego Paivas. Yes. Okay, that is going to talk about experimental investigation of geometric quantum speed limits. The word's yours.
So, can you hear me? Oh, I would like to thank the organizers for the opportunity to be here and talk about this work. Before starting about physics, I would like just to show you the place where I came from. And right now I'm a professor at São Luís. As can you see, it's a bit far from here. São Luís, it's a nice place. If you have the opportunity to visit us, we have a nice city, a nice bars, and the most interesting thing in this cultural part is the São João party. I mean, it often takes 2 months. It starts in the end of May and it ends on the beginning of the August. And as you can see, we have a lot of nice food, shrimps, and this rice here that they call arroz com puxá. It's a nice food. And here we have the açaí, but it's the true açaí. Of course, you can find açaí here, and I respect. But this açaí here is completely different because here we don't have these toppings that you can find here, but it's you can taste this açaí with some kind of oops, a bit. You can taste this açaí with some kind of cassava flour. It's nice. And of course, if you have the opportunity to visit us, you are more than welcome. And we also have this beautiful place, the Lençóis Maranhenses. This is a national park recognized by a few months ago. It's right now, let's say, a World Heritage Site recognized by UNESCO. So again, if you have the opportunity, please visit us. So let us move to the business part of the talk. And here I have some outline. And the main idea is to cover the basics about the speed limits, but just the basics regarding closed quantum systems. I mean, discussing the main results, the seminar results. Then I would like to move to our contributions in this subject. I mean, this geometric perspective. And then I expect to conclude in time discussing this experimental investigation. And I need to be honest, I'm not an experimentalist. Maybe I'm not the right guy to be here talking about this, but I will try. And then what is the main idea? Well, you can ask yourself about this. I mean, you have a lot of motivations. What is the role played by time in quantum mechanics? I mean, position, momentum, energy, they are operators in quantum mechanics, but you cannot have, I mean, at least in standard quantum mechanics, you cannot have an operator, a Hermitian operator related to time. And of course, you can ask yourself about how fast the quantum system evolve under a given quantum dynamics. And the interesting thing about this discussion is how can we relate this time conundrum with the distinguishability of quantum states? And that's it. What about the main results, the seminar results? Well, I should mention the Mondestan bound. And the idea is the following. Suppose you have a closed quantum system, a finite dimension system. And we start with some initial state. You have this initial state. And for example, for simplicity, let us set time-independent Hamiltonian. Then you have the unitary evolution, and you have this instantaneous state. And you ask yourself, what is the minimum time in which we have the initial state orthogonal to this state psi of tau? I mean, suppose you have the evolution starting from t equal to 0, and the system reaches this state psi of tau at some time t equal tau. And after doing some math, I mean, supposing that you have this constraint, this orthogonality condition, then you arrive in this expression. I mean, this time of evolution is lower, this time of evolution is lower bounded by this quantity. This is the quantity that these two guys call it somehow as the quantum speed limit time for closed quantum systems. If you apply this constraint here, I mean, the interesting thing is that this lower bound scales with the inverse of the variance of the Hamiltonian. I mean, the generator of this unitary dynamics. In the literature, you may find this result discussed in a paper by Aharonov and Anandan, exploiting the geometry of pure states. And the idea is that the evolution of the system draws a path in the space of quantum states, and the result is the same. This is let's say, the first result on this subject. You can relax this condition, the orthogonality, and if you ask yourself the same question, but relax this condition, you consider non-orthogonal states, then you arrive at this expression. I mean, this time of evolution is lower bounded by this expression here. Again, it scales with the inverse, the fluctuations of the Hamiltonian with respect to the initial state. I mean, it's a unitary evolution, and then it does not matter if the variance is calculated with respect to the initial or the instantaneous state. But it appears this quantity measures, I mean, indicates the distinguishability of the two states. I mean, this R cosine is nothing but the so-called Ullmann fidelity for pure states. You see that when these two states are orthogonal, then this quantity is equal to 0. Then this R cosine gives you the pi over 2, and you recover this expression here. So the fluctuation of the Hamiltonian is calculated in this way. Well, around 50 years after this Mandelstam unbound, these two guys addressed the same problem, but using different techniques. I mean, looking to the same problem by in a different perspective. They arrived at a different result, and then the point is, you have again a closed quantum system, unitary evolution. You have the system is prepared in an initial state. Here they have considered the spectral decomposition of the Hamiltonian. I mean, you have a finite dimension system. You have the energy levels, the eigenstates. And for simplicity, they consider the ground state has 0 energy, but you can relax this assumption, and you can expand the initial state in with respect to the eigenstates of the Hamiltonian, and by playing with the math and applying again this orthogonality constraint, you arrive at this inequality. Interesting, the bound that they get scales with the inverse of the mean energy of the Hamiltonian with respect to the initial state. Just to let you know, if you relax this hypothesis here, we should have the mean energy minus this ground state energy. And this is the quantum speed limit time derived by Margulis-Levitin. The funny thing is that, as I told you, this this lower bound on the time of evolution scales with this quantity, this mean energy, instead of the variance of the energy. And quite recently, it appeared a paper where the authors addressed the so-called dual speed limit. I mean, instead of assuming you have a lower bound on the spectrum of the Hamiltonian, you consider that the spectrum is bounded from above, and then they find a lower bound in a similar way, the same spirit that the Margulis-Levitin, but here they found the highest energy level minus the mean energy. So we have two bounds, and it's quite confusing. How can we put these bounds together? How can we conciliate these two results? Then it came this unifying bound. This is the bound addressed by Giovannetti, Lloyd, Macone, and Tommaso Toffoli, and Levitin. Well, the setup is the same. If you apply again this orthogonality constraint, you will find that the unified bound is given by this maximum between the two results. It seems to be quite controversial, because if you have two lower bounds, why should we take the maximum between them? And the idea is more or less simple. Suppose that one of these two bounds is equal to 0. Then you just get the non-zero lower bound to be this tau QSL, this speed limit time. And you can also discuss the situations in which this bound is tight. And then we have, well, when the variance and the mean energy, the ratio between them is equal to 1, we have the bounds are identical and achievable. And when these do not happen, we need to consider this more carefully. Well, after these two results, in the literature had appeared a lot of papers addressing more complicated situations. I mean, you have papers discussing situations like mixed states, time-dependent unitary evolutions generated by time-dependent Hamiltonians. We can relax this orthogonality constraint, and of course, we can investigate this problem in the context of open quantum systems. Then we have this kind of QSL zoo. I just put here the red line of some of the papers. Of course, there are a lot of papers addressing this. We have a lot of contributions discussing these QSLs from open systems to closed systems. And but the question is, we have a lot of them, and how can we generalize these results in some way? I mean, how can we try to put these results in some way together? Then around 6 years ago, in collaboration with these guys, I mean, most of them are in the audience, we published this paper, and the main idea is the following. How can we generalize these previous results on QSLs? I mean, how can we get a bound for QSLs that take into account unitary and non-unitary evolutions? How can we take these bounds in a general theoretical formulation? In some sense, how can we discuss the lower bound on the evolution time for a general physical process? And how can we put this distinguishability of quantum states in a clear way? And what is the idea? The idea is, well, when you have the set of the states, you have this space of quantum states. Each state can be seen as a point in this manifold. And suppose that here we have the initial state, and after some time tau, the system reaches this final state at some time t equal to tau. And if the evolution of the system that can be generated by an arbitrary operator, general dynamics, if you can think in this way. The dynamics of the system evolving draws a path in this space of quantum states. And for example, here we have a given state, given instantaneous state, and we have this neighbor state just by shifting from time t to time t plus delta t. And if we know how to distinguish these two states in this, let's say, this infinitesimal perspective, look into the neighbor states. If we know how to do that, we can integrate along this path, along all the path related to the evolution of the system, and we have a way. We have some technical way to address this distinguishability. And by using this distinguishability, we can extract the evolution time for some general dynamics. Here I have the basic setup. I mean, we start with some density matrices. We have these basic conditions for density matrices. And the point is, how can we distinguish two neighbors state in this manifold? We use this Morozov-Chenkov-Petz theorem. I mean, the distance, the infinitesimal distance between neighbor states is given by this expression. Here we just have the populations of let's say the perturbed state with respect some basis. And here we have this funny contribution that comes from the coherences. If you keep track, you will realize that this contribution is indeed related to the coherences of the state of the system with respect to some basis. Well, these C functions are given in this way. I will skip most part of the details, and what can I say you is that we can select some functions in a formal way in order to set some kind of distinguishability measures, and in the end of the day, each of these function you give you a kind of inner product. I mean, in the end of the day, this distinguishability measure is nothing but an inner product in order to compare two different states in this manifold. For example, this first contribution is completely related to the Fisher-Rao metric, somehow related to the previous talks that we have today. This formalism finds applications in quantum thermodynamics, coherence measures, and of course speed limits. And well, if you know how to evaluate this quantity, again, you sum over all the path, and you play with the math and extract the time of evolution, and that's the idea. But the point is, suppose the system evolves following this path. Of course, this is a general path. The evolution can draw any path between these 2 points. Of course, there is some path that exhibits the shortest distance between these points. And if you think in the same way that the least action principle, you can write down this inequality. I mean, this calligraphic capital L is just the length of the, let's say, the geodesic path that connects the initial and the final state. And then you have this small l that defines the length of some general path connecting these two states. This length is calculated by using the infinitesimal distance that I have shown in the previous slide. And this capital calligraphic L is somehow evaluated by optimizing this quantity here. And then I just write down the two contributions, the contributions related to the populations, the diagonal elements of the density matrix. And here I have the contributions that come from the coherences of the state. And if you solve this inequality, you can find this time of evolution, but it's quite difficult because if you look carefully, you will realize that this inequality depends on several quantities. Especially, it depends on this function that gives us the idea of the inner product related to the way in which you distinguish the states. And in this way, we can play with a different quantity. I mean, we can put this relative error. This is the figure of merit in which we will look to this speed limit time. I mean, when this quantity approaches zero, we just set this speed limit time because if you look carefully, this quantity approaches the geodesic length performed in the evolution. Again, you need to optimize this quantity over all the set of information metrics, the inner products that you can define over the manifold of the space of quantum states. And again, this is quite difficult to be done. And because of this, we just select two of these information metrics. One of them is the quantum Fisher information. The other one is the Wigner and Askew information. And just to give you an idea of the results, here we have the example for unitary evolution. We applied our results and find this lower bound by using the quantum information, the quantum Fisher information metric. This is quite similar. Well, this is quite similar to the Mandelstam bound. The difference is that here the generator is time dependent. Here we have the result for Wigner and Askew information, and here we have some results trying to address the tighter lower bound. And for a single qubit, we just realized that the tightest bound is given by the quantum Fisher information metric. Well, for non-unitary evolution, we investigated the case of amplitude damping channel. We have analytic expressions. We have this. We have these results for quantum Fisher information metric and Wigner and Askew information. I mean, these results are quite complicated. Here we have, for example, this elliptic integrals, and then you need to consider this numerically. And then we have these plots. And the most important plots, in my opinion, are here. This red curve refers to the quantum Fisher information metric. And this blue curve is related to the Wigner and Askew information. And then you find that for this evolution, Wigner and Askew information provide the tighter bound. Well, then we have in the last 2 minutes the experimental investigation. As I told you, I'm not an experimentalist. The results has been published a few months ago. Here we have the people involved. The guy that conducted the experiment is this one, Jefferson Figueiras. The experiment was done in São Carlos, in Brapa. The idea is use this NMR setting that Alexandre explained in this morning. And we have this chloroform sample. We have this nuclear spins In the end of the day, we have a system of 2 qubits. These qubits are encoded in the spins of the carbon. And again, the hydrogen plays the role of a bath. And well, I will skip these details, but the point is, here we have the plots. Well, we can model the dynamics of the system by using these Krauss operators here. I mean, it's nothing but the phase damping channel and a bit phase flip channel, and the results are here. Well, in these plots here, we just have this relative error, and here in this column we have the results concerning Fisher information, and here we have the Wigner and Askew information. And in the more 5 seconds, we cannot see so much difference between the results. And then we just evaluate the difference between the relative error concerning Fisher information and Wigner and Askew information and find these results here. And if you look carefully, this difference is quite small. I mean, 10 to the power -2, -3. And in each panel here, we have a kind of concentration of the molecules of the chloroform. I mean, in the end of the day, we add some impurity in the sample to control the relaxation times. And well, the take-home message here is, although in the theory, we have some special considerations about these inner products, the distinguishability measures that you use to derive the speed limit. But in the experimental level, this difference is quite irrelevant. Well, if you are interested, we can discuss later. I have some interesting things to say about non-Markovianity here, but I do not have more time. So I thank you.
Thank you, Diego. We have time for questions. There is one there.
Thank you for the talk. So I didn't get, how do you convert the length to time? Because you started with a metric, right? And then the second question is, once you have the geodesic, how do you guarantee that there is a dynamics that generates that, a quantum dynamics that generates that connection between the 2 quantum states?
Well, let's start from the last question. Well, this geodesic, you can prove that is indeed related with this measure. I mean, for each metric, we can prove that you have a geodesic length. Then for a given dynamics, you can calculate the geodesic length and let's say the length related to the actual path followed by the system. That's it. And the first question is about the time.
How do you relate the length to how you convert length to time? Because you
okay. Well, if you know how to solve this inequality, you are okay. I mean, of course you can plot the left side and you can plot the right side as a function of time, and then find let's say the points in which you saturate the inequality. But this is difficult. You can do with this numerically, but it's not so interesting. I mean, actually, you can use some tricks that people usually apply in the papers and multiply by some tau and divide by some tau and define some mean energy or something like this, and it's okay. But the point is, you can, in our perspective, it's more honest, if I can say, to build up this quantity that signals the time in which you saturate the inequality, and the time in which you saturate inequality, you should have this speed limit time. I mean, as long as you guarantee that this difference approaches 0, you have this speed limit time.
So as I understand, one of the nice things about this sort of geometrical formulation of the speed limit is it shows that, you know, kind of quantum speed limits don't have to be quantum, right? They hold equally well if you have some Markovian stochastic process, right? So, I mean, in the end, then you show that like there's not really any difference depending on the metrics that you choose. But to me, this kind of signals that the eigenvectors aren't changing. Is that correct? In the NMR setup. So like if the the eigenvectors aren't changing with time, so this would.
Could you say again, please?
So I mean, if I don't have coherences at all, right, which is I guess somehow to me seems very kind of NMR like. It just seems that everything is in the classical part anyway. Is that the reason why there's no real difference in the end depending on which metric you choose?
Yes, but the point is, well, we have coherences in this case. I mean, in this, well, if you let the system evolve, at some point the signal just disappears, and of course you do not have coherences anymore. But here we have coherence and populations, and we have this kind of competition. Well, you find these oscillations here because in this plot here we have no Markovian signatures. I mean, you have this kind of backflow of information. Then this case refers to some situation when you add some ferromagnetic impurity in the sample of chloroform molecules. And then you, in some way, you can change the relaxation time of the sample of these nuclear spins. And then when we increase this parameter, this concentration, you can go from the situation of non-Markovian to Markovian. That's what you can see in this plot here.
So do you think like you can kind of modify just to say probe classical speed limits?
Yeah.
Okay.
Yeah, I think so. But again, I'm not an experimentalist. I'm not the best person to say how can be easy or not.
So in the unitary case, you only need to specify the first two moments of energy, and you can derive the time of the fastest dynamics, and you don't need anything else. In the open system case, you basically need to solve the whole dynamics, compute the density metrics in time, integrate some functional of the density metrics in time. So you already have to know the time. And from that, you can derive time as a function of time.
Yeah, it's a.
Like why?
Yeah, it's a, yeah, but yeah, the point is, well, your question is, why do I need a bound that in the end of the day, it's so complicated as the initial problem?
What is the physical meaning of the bound?
Well, the main idea is just if you don't know, well, of course, you are right. For this case, I can agree that the formulation is so complicated in this manner, but you can try to derive some lower bound that depends on minimal ingredients. Let's say just knowing the initial state and then knowing the generator of the dynamics. And we have in the literature situations like this. But of course, this is
so
not
like
the best
this is like approaching the most general case, but in some specific case.
The idea is well, the PRX we provided the mathematical formulation, and here we just provide the experimental realization of the results.
Thanks.
Just trying to answer your questions about the interpretation. That said, the speed limit that Diego used on the PRX can be reformulated in terms of the Kramer-Hall bound. So it's in certain way, he's generalizing the time-energy uncertainty relation, and then we can think about estimating time. So it's when we generalize the for the idea of the Kramer-Hall bound, then we can talk about the speed limits. It's very natural in his approach.
Just a final message. This formalism can be used to investigate problems in quantum metrology, quantum thermodynamics. For example, if you have a set of space of parameter space as a temperature magnetic field, you can use this formalism to consider, to treat these systems. This is quite general.
Okay, so let's thank again for Diego and all of the speakers. And then we have a short break now. We have the coffee break outside waiting for us. with Adalberto Varizzi talking about entropy production from maximum entropy principle. So thank you. The word is yours.
Okay. So hi everyone. Good afternoon. So I'm gonna talk about entropy production and how we can use the Jane's maximum entropy principle to construct formulas for this quantity. But first, let me also talk about where I'm coming from. So I'm a postdoc at the Universidade Estadual de Santa Cruz in the city of Ilhéus, which I show some pictures here. So in the first picture, we have the city's cathedral, and in front of it, we have this golden boy here, which is a statue of the great Jorge Amado, who made the city famous in his books, and which, because of this, gives his name to everything there, except for the things that are named after Gabriela, which is his most famous character. And so to give an example of this, in the second picture here, we have a humpback whale jumping in front of the Jorge Amado Bridge in the background. And here again, we have the Jorge Amado Bridge with the sea of Ilhéus in the background, which is better than the sea here in Rio, because here the water is cold, and there the water is very warm, very pleasant. So, okay. I guess Pedro, who will speak next, will have more to say about the city. I don't have a map here, but I guess he has one. So, okay. So first, I'm going to talk about the problem we are approaching here in this work, which is that of defining entropy production. Then I'll give some examples of definitions of this quantity, and then I will show how we can use the maximum entropy principle to construct definitions and to kind of join some of these definitions that we found in the literature. So I guess the audience here is familiar with the formulation of the second law in terms of an entropy production. So the second law, we can basically state the second law as the entropy production in a process can never be negative. So it must always be positive or zero, and zero if a process is reversible. But thermodynamics is a funny theory because it tells us that the entropy production must satisfy this property of being non-negative, but it doesn't give us a function to calculate this quantity. It doesn't give us a formula for the entropy production. So there has been a lot of work dedicated to constructing this function, trying to build these formulas and expressions for this quantity, the entropy production. So here shows some papers doing this, just a small amount of paper doing this. So in various contexts, sometimes more general, sometimes more specific. So I will talk about some of these definitions later on. So I'm sorry. So what we did here in this work was to give a new definition, but this time using the maximum entropy principle. And perhaps more importantly, what we show is that several of the previous definitions found in these papers I showed before can be connected using this principle and can be derived from it. So, okay, before showing how we did this, let me present some examples of definitions of entropy production. So I will start with this diagonal entropy production, which appears in this paper by Polkovnikov. So the scenario considered here is that of a closed quantum system evolving unitarily with a time-dependent Hamiltonian, and it is considered that the initial state is in it's diagonal in the energy basis. So what Polkovnikov proposes here is that we use this so-called diagonal entropy which is given by the Shannon entropy of the energy populations of the system, as a definition of thermodynamic entropy. And its reasoning is that when you have a big system and you're making some measurement of it, you are intrinsically making some time average, because usually the time you take to measure the system will be much larger than some internal time scales. So you're inevitably making some time average when you measure the system. And when you do this, what matters are the populations, are the energetic populations of the state. So that is the motivation for using this diagonal entropy. And then if you assume then an initial state which is diagonal in the energy basis in such a way that the observer making these measures can know these populations, then we can show that the diagonal entropy at later times will always be bigger or equal to the diagonal entropy at t equals 0. And then if we define an entropy production as the difference between the diagonal entropy at some time t and some initial time 0, then this quantity will be always non-negative as required by the second law. So as another example of definition of entropy production here, I showed this observational entropy production, which is discussed to very much detail in this paper here. Sorry. Okay. So again, the scenario is that so again, here the scenario is that of a closed quantum system evolving unitarily with a time-dependent Hamiltonian. But now the argument is that as systems become bigger, the spacing between energy levels become really small. And so you can no longer distinguish between them. And so when you're making an energy measurement, you cannot really associate what you're measuring with a single energy eigenvalue. And then what you're really doing is what you can really say is that you find in the system in some energy shell with the energy in some range, which is related to the precision of the measurement. And so mathematically, we can associate to these energy shells a sort of energy trajectory, but a big one with a volume bigger than one. So if now we start with the initial state, which can be simply stated in terms of the probabilities of finding the system in different energy shells, then you can prove that this so-called observational entropy, which is given by the Shannon entropy of the probabilities of finding the system in different energy shells, plus a term related to the volume of these energy shells, then you have that this observational entropy at later times will be always bigger or equal to the initial observational entropy. And again, if we define then the entropy production as the difference between the observational entropy at some time and the initial observational entropy, it will again be non-negative. The observational entropy can also be applied to open system. In this case, it is usually considered that the coarse-grained energy measurement is made on the environment, while it is usually also assumed that the system of interest can be measured with arbitrary precision. So you can, for instance, measure it in its own eigenbasis. So then if we define the observational entropy as the Shannon entropy of the probabilities of finding the system in a given state while the environment is in a given energy shell plus
a term associated with the volume of the environment energy shells, and the initial state is such that the system and environment are initially uncorrelated, and the environment is just the state of the environment is just defined by the probabilities of finding the system in different energy shells. Then again, the entropy production defined by the difference between these observational entropies at some time t and time 0 will be non-negative. And finally, as a last example, I consider here what I'm calling the correlation entropy production, which was proposed in this paper by Exposito, Lindenberg, and Vandenbroek, which is also the one used in this review by Gabriel and Paternostro. And the scenario here is again of an open system, evolving unitarily, the whole evolving unitarily. And now here we consider an initial state that is separable, and as the system evolves, the dynamics will create correlations between system and environment. It will usually change the state of the environment, but if we consider an observer who can only make local measurements on the system, then we will have, he won't be able to say anything about the correlations that are being created and about how the environment state is changing. And so we can associate an entropy production to this, which will be given by terms of quantum relative entropies here, which with each contribution here being related with these non-accessible correlations and non-accessible state of the environment. So given these 3 examples of definitions of entropy production, we can ask, why do they differ, and why do they differ, and what do they have in common? So starting by the distinctions between them, what really makes them different is that each one assumes an observer with a different capability. So an observer able of measuring different things. So for instance, in the diagonal entropy, the observer can only know the energy populations. And in the observational entropy production, what the observer can measure is in fact, or know, is only a coarse-grained version of the energy populations of the system. And finally, in the correlation entropy production, the observer can only make local measurements. So they are different because each assume an observer measuring different things. So, and in what they are common in the fact that each one assumes a very special initial state. And each one assumes an initial state that is compatible with what the observer is able to determine. So for instance, in the case of the diagonal entropy production, what the observer can determine are the energy populations. So they consider an initial state that is diagonal in the energy basis. In the case of the observational entropy production, what the observer is able to say are the probabilities of finding the system in different energy shells. And so the initial state is fully constructed by these probabilities. And in the correlation entropy production, since the observer can only make local measurements, it is assumed that the initial state is separable. So what it did was trying to join these features and construct a more general definition of entropy production. So we consider here a system and an observer who can who has access only to a limited set of observables, which I call here this set X. And we assume as before that the initial state is such that being able to measure just this set of observables is enough to completely determine the system state. What I mean by this is that if you measure this set, we will get these expected values, and the initial state here can be a function only of these parameters. So, okay, then as the system evolves, here the system can be closed or open, but if open, the whole, you can see that the whole evolves unitarily. So as the system evolves, the set X will in general not be enough anymore to determine the initial state at later times. But okay, but given this set of observables, what can we say about the system state? So again, we suppose we measure this set, so we have the expected values of them. These expected values usually won't be enough to say what is the evolved state of the system, but you can still use them to try to build a state, try to infer and attribute a state to the system. So what the maximum entropy principle says is that we should attribute to the system the state that maximizes von Neumann entropy given the constraints of the known expected values here. So if we do this, if we try to solve this problem, we will obtain a state which has this Gibbs-like form, where the Greek letters here are such that it ensures that the maximum entropy state, which we are attributing to the system, is equal to the measured expected values. So, okay. So with this, since this X here generally don't completely determine the evolved state of the system, the maximum entropy state will be different from the evolved state. And then we give a definition of entropy production, which is the entropic distinguishability between the actually evolved state of the system and the best guess an observer can make. So, okay, this is our definition. So with this, what can we do? So now, if we consider that our set of accessible observables are energy projectors, then with this, what we can say about the system state are the energy populations. So in this case, our definition reduces to the previously shown diagonal entropy production. On the other hand, if we consider that, in fact, our accessible observables is a projector of some energy shell of the system, then our definition reduces to the observational entropy production. And finally, if we assume that the set X is that of the local observables of the system, then we recover what I call the correlation entropy production. So, okay. So then what we see is that the maximal entropy principle gives us a way to construct general and adaptive formulas for the definitions of entropy production. And it allows us to recognize why there are these different definitions in the literature, and they are different basically because they are implicitly or sometimes explicitly assuming different things, observers capable of different things. And Thiago said earlier that we have a zoo of definitions of work in the quantum thermodynamics community. Now it seems that we're starting to have a zoo of entropy productions. So I guess it was interesting to try to build some cage for them. We'll try to bring them together. So yes, I will end now. So I thank CAPS and CNPq for allowing me to pay my bills. And I thank you all for the attention.
Thank you, Adalberto. Questions?
Yeah, I'm entirely not in the field, so maybe, but when you describe the three, let's say, entropies that you introduced, it looks that two of them are really like one a modification of the other. Wait, the third one looks completely different. Is it correct?
But the first one you can see as a particular case of the second. Okay.
Exactly.
Yes.
Instead, the third one is completely different. Am I
Yes.
right? Okay. And the other thing is this maximum entropy principle is, let's say, somehow based on the idea that that is the most probable state compatible with what you know, or what is the rationale for choosing that state?
It's the best guess you can make that is unbiased on what you can know about the state.
So let's say based on what you observe, any state compatible with that diagonal is equally probable. There is not a state that is more, let's say let's assume that in a certain eigenbasis, you are fixing the diagonal elements by this, and you have the coherences around. Now, the fact that you put all the coherences to zero is just conventional. You could have other stuff, right? There is not a, how can I say, a probability like say, okay, no, having zero coherences is most plausible than other things. No.
It's the best. It's the maximum entropy state. It's the one which is unbiased. It's the best guess you can make that it's unbiased.
Okay.
Thank you by the talk. Maybe I missed something, but sorry. What happens if the set of observables are enough at time t to describe the whole state?
Then the maximum entropy state will be the evolved state, and the entropy production is zero.
So you said in the beginning that despite we don't know the expression for the entropy production, there are thermodynamic constraints. For instance, if you evolve in the quasi-static limit, it has to go to zero. So did you check if these four definitions of entropy production you get really go to zero in the quasi-static limit?
The papers defining them do. So I did not check that because they checked it before.
Thank you. I actually had a similar question to what Marcus just asked you, but I want to make this a little bit stronger. So most of these notions of entropy production that we're working with seem to be very much inspired by information theory or quantum measurements or something like this.
Yes.
What I've been wondering for a while now is when you think about entropy in thermodynamics, you actually come completely from the opposite angle. So you have resources that you exchange with the environment, some you can control, some you cannot. And then entropy is introduced, the Clausius entropy is introduced as the line element of the uncontrolled exchange of energy with the environment. Do you think that any of these notions of entropy production could be reduced to something like a thermodynamic interpretation?
Yeah, I'm not sure if I understood the question. Sorry.
So let me rephrase those a little bit.
Okay.
So the way that I think about entropy, entropy starts in Clausius's work as by the attempt of identifying the line element, the exact differential that describes the non-exact differential heat. And all of the thermodynamic constraints, such as that the entropy production has to go to zero for quasi-static processes, arise from the thermodynamic considerations. Now, in statistical mechanics, we define entropy essentially as the Shannon information of the Gibbs state or the Gibbs entropy, and then we make this a little bit more general and account for other levels of information that we have about the system. And this is the background of the Shannon information, the von Neumann entropy, and all of that, which underlies all of these definitions. Now, in quantum thermodynamics, for the last, 30 years or so, we've been defining different notions of entropy production that are all very much motivated by interpretations of entropy that come out of information theory. And I'm just wondering, how do we connect back to thermodynamic interpretations of entropy? How do we get back to line elements of heat?
Yeah, I don't know how to answer that.
Perhaps you can discuss better with him later. Any more questions? Okay, if not, so let's thank again for Adalberto.
Vou colocar tamanho de barra, senão tem.
Okay, so okay, so the last speaker is Pedro, that is going to talk about canonical typicality under general quantum channels. Okay, the word's yours.
Okay, thank you. Can you hear me? Okay. Okay, good evening, everyone. First of all, I would like to thank the organizers for inviting me and making this event possible. So before I get started on the talk, I'm going to present again Ilya's How with a Map. Oh, we have a very big screen. It's looks even better now. So here is Ilya's, and even better, there, you can go visit us. So here, Rio de Janeiro, we are quite 1,000 kilometers from here. So Ilhéus might not be Rio de Janeiro, but we also have a Christ. But it's a way better. Instead of on the top of high mountain, our Christ has a beach, okay? With cheap prices as well, okay? So come to visit us. So I'm a professor at UESC, Universidade Estadual de Santa Cruz. This is our charming campus, is surrounded by a tropical forest here. We have a recent postgraduate program in physics called Profísica, and an even younger, maybe 1 year, quantum information group called NEMES, Núcleo de Estudos em Mecânica Estatística, Mecânica Quântica e Sistemas Complexos, composed by 2 permanent members, myself and José Geraldo, an external researcher, Ana Sproch, from Federal University of Paraná, and Alberto Varize. Okay. So the work I'm gonna present to you today, it's canonical typicality under general quantum channels, recently published. And this work was made in collaboration with Gabriel Dias Carvalho from UPE, Pernambuco, and from Rio de Janeiro, Tiago de Oliveira from UF, Raul Valejos, and Fernando de Mello from CBPF. So basically, our work taps on the foundation of statistical mechanics. It has a very simple idea. You're going to see that I can explain everything just with figures. I put just some equations to look like more professional. So let's start by some that you know, the idea what means canonical typicality and how it connects to foundation of statistical mechanics, okay? So starting from the this screen is so big, I cannot really see it. From textbook statistical mechanics, we learned just since the graduate courses that statistical mechanics bridge 2 regimes of descriptions, the macroscopic thermodynamics and its microscopic descriptions, right, given by quantum or classical mechanics. And basically, the success of statistical mechanics is grounded on the ensemble formalism, right? Where the thermodynamics properties can be calculated as average on microscopic ensembles, right? And yet on textbook statistical mechanics, we usually see that the first principle of such a formalism, sometimes called the fundamental postulate of statistical mechanics, is the principle of equal a priori probabilities, where basically we have for an isolated system with fixed energy, we assign the same probability for all microstates with that same energy, right? So it directly defines the microcanonical ensemble, in which you have the probability of each micro possible state with that energy is 1 over the number of micro states with energy R, okay? And if now we consider the case that the system is not more not isolated anymore, but in contact with some thermal reservoir, we can understand the situation by our system being a very small system in a very large global system, right? And from microcanonical, we can derive the probabilities distribution here. Now we have fluctuations in energy, and considering the weak interaction between our system and our environment, we can arrive at the so-known Boltzmann-Gibbs distribution, the canonical distribution, right? So we can ask them, so these questions are posed since the roots in quantum mechanics, why we use equal probability a priori, why this principle? In other words, why ensembles works, okay? Because in experiment, we don't have ensembles, right? But ensembles are used to describe such situations. So there are some traditional justifications, for example, the maximum entropy principle. Adalbert just tell something about that the probabilities are assigned to maximize the entropy under known constraints, and sometimes a more physical justifications. For example, basically this one on classical systems, ergodic and chaotic systems, where the dynamics ensure that all accessible microstates are sampled equally over time. So in fact, we have a phase space. This could be our macro state, that is our energy. And here, for each point, I do have the water here. If I look at the micro state, they evolve with this ergodic situation. Every time I pick this microstate, they will be in the typical scenario, represented by the microcanonical ensemble. Another kind of justification is using typicality arguments that are dated, again, since Boltzmann, but nowadays there is a renewed motivation, basically with the development of quantum information theory. And on quantum information theory, what means typicality? Most pure states in large quantum systems naturally align with ensemble average. So this is some of the seminal papers. So we have a bunch of them nowadays. And we're gonna look more precisely to these ones, the Popescu paper, where they justify typicality to describe the canonical typicality, the canonical ensemble. So we'll get into details on this because we are, as you see, we're gonna generalize in a very simple way and very strong too. So it's worth to see that. So this article is titled as Entanglement and the Foundation of Statistical Mechanics. Here, they said that principle of equal a priori probability is actually apparent. So the canonical ensemble arises from the entanglement between the system and the environment. Let's see how this works. So first of all, let's rewrite the ensembles in a quantum way, in quantum information way. So our microcanonical ensemble will be given a restriction that could be anything, but let's put the energy here, will be the maximally mixed state in this restriction, where this is a projection on this subspace, and dr here is the dimension of the restriction. So we can straightforward define the canonical state, which will be basically applying the partial trace over the equiprobable state. So this one will be our canonical state here. Have a look that the partial trace have this fundamental role here that they map the universal space here to the space where there is our system. Okay, and you call system here the degrees of freedom that you have access. This scenario, the local degrees of freedom that we have access here. So basically what they showed, they said the principle, the equal priori principle probability is apparent, and they changed this for a different principle here, which they call general canonical principle. They said that given a sufficiently small subsystem of the universe, almost every pure state of the universe is such that the subsystem is approximately in the canonical state. What they mean by that? No? I can assign to my system in the restriction a random pure state and look at the subsystem, and almost every pure state, a reduced pure state from psi will look very similar when we'll apply the partial trace over the acute probable state. So they demonstrate that for the majority of pure states on the global, we arise to a description given by the canonical. So we don't have necessarily start from the principle of equal probability a priori, which defines the macrocanonical state, to have a description looks like a canonical one. So here the principle of equal priori then is apparent. Almost every pure state of the universe, this psi here, is locally on the subsystem indistinguishable from the probable state. More technically, what they did was derive an upper bound on the average distance, here distance as the trace distance, taking the Haar measure here on psi, and you see that when in fact, when the subsystem is very small compared, for example, for the effective dimension of the environment, this bound will be very tight. So we can show that in the average, this value goes to approximately 0. And the other part of the proof is using some kind of law of larger numbers for quantum Helm, which is Levy's lemma. And they demonstrate that the probability that given a random psi here, this distance between these three states deviates from its means, that it's already small, by some little epsilon, that and this deviation decays exponentially with the dimension of the global system, the restriction, right? So that is the main result. So what means canonicality? Now we can to demonstrate the why canonical ensembles works. In fact, it's because pure states of a global state locally already looks like canonical states, right? And in some sense, this is their arguments that we can choose a principle that you can somehow demonstrate its physical meaning, right? And the entanglement is because if I have a pure state on the global, the reduced state that looks like a canonical state with mixture, we have to have entanglement here. So the canonical typicality must take account the entanglement between system and environment. So this is kind of figure of merit of this approach. Now we're going to generalize this result in a kind of simple way, but as I said, in my opinion, very strong, by generalizing the concept of subsystem. Right? Note that everything I discuss here, when I look at the subsystem description, this can be very general, not necessarily in a thermodynamic approach. The system, or if I have a global space, I can separate between the degrees of freedom that we have access to and the degrees of freedom you don't have access or you don't want to care about as system and environment. And our subsystem will arise our description. So we have access to a well-localized portion of a global system, this one. And the degrees of freedom here can be identified as microscopic components of the system, okay? We can add also some unitary transformation here, but unitary transformation will not change this tensor product structure. However, we can think beyond that, for example. We can think that the degrees of freedom that you have access to a system are some kind of diffuse portion of a global state. We don't have this well-localized portion that we call the system. But can be some diffuse portion. So the degrees of freedom can be effective components. This one is just illustrations. We are not meant to describe proteins here. I think physicists, maybe one day, my grandson, I don't know. So they already do that. For example, to study such difficult proteins, they assume some kind of effective degrees of freedom here to facilitate the computation and describe what they want. So this can be our choice or can relate to our possibility or our capacity for interact with the system. And in a quantum information perspective, we can describe such kind of what we are calling here by generalized subsystem, employing the quantum channel approach. So, which are completely positive trace preserved map, which maps now our global space, which not necessarily has this structure, to a space with our degrees of freedom that you have access to. So this term here and saying that is defined by quantum channel, it's not new, appears here. But as far as I remember in the context of thermodynamics, I didn't see them doing that. And just to give more a flavor why we are choosing to, why we calling this generalized subsystem, we can look at a special representation of any quantum channel, which is the Stein-Spring representation, in which basically is a mathematical rearrangement of the degrees of freedom in an extended Hilbert space. So any quantum channel can be described also as a partial trace. But first, we need to apply some isometry here that will extend my initial state on the universe. And then we can trace out this environment, which is usually a mathematical abstract environment, right? Don't have this, we have our system. We don't have a system environment structure here, but applying this V, we can have this structure where this system will be our generalized subsystem, and this will be we can call this the generalized environment, for example. And using that, what we show, this is a concrete example where there is such a maps that describes such kind of situations. In that case, is a toy model intended to describe blurry detection in a cold atoms optical lattice scenario. In this, I'm gonna just describe a simplified way where, for example, two atoms here, we don't have a potent microscope that can discern where are the excited states and where coming from the light between two neighbors, for example. So it can be possible to construct such a quantum channel that did this map. So if I'm seeing no excitations, I will map this state to 0, 0, 0 to 0. If I have excitation on the right, on the left, on both, our microscope beyond blurred is saturated. So the only thing that I can say is that there is some excitation there. So we can construct this map, and from here we can see that we cannot do this by using partial trace, right? Here, okay, you can use partial trace, but here we cannot. And not even if you fix, for example, you can say, well, I can apply some unitary operation and rearrange this degree of freedom, but there is no unitary operation that can do that, right? Transform into partial trace. So you need a more general way to describe this kind of generalized subsystem, okay? So since I present the canonical typicality, and now a generalized subsystem is quite straightforward now to generalize the canonical ensemble, for example. We begin by describing our microcanonical ensemble, and the generalized canonical ensemble will be simply by defining, instead of using partial trace, which is the usual case, we apply this channel that will describe your access to the environment, to the system, okay? And what you did for prove that this general canonical principle also holds for this generalized subsystem. That is, just repeat, given a sufficiently small subsystem of the, sorry, I didn't mean to do that, but what the sentence here is valid only for the first canonical principle. But when generalized, we can also pick random pure states here, or described by the microcanonic states, and the generalized subsystem description of both a random pure state of the microcanonic states, they will be closer, okay? And now we change the figure of merit here. Now our upper bound will be related to some kind property of the channel that will be changed dependent of the channel that we choose, which is the purity of the choice state, or in other terms, in terms of the entropy of the map. Okay, let's analyze a little bit more this result. Just remember, for you that don't know, that every quantum map using the Minkowski isomorphism will have a representation that is a state. So we can study properties of the map, look at the properties of the state, the choice state, right? Where this psi here is the maximum entanglement state in the RR space, and we apply in the first part of the system, our channel that we want to describe. So as you can see, by the definition of the choice state, you can define the entropy of a map, which is simple, is the linear entropy, which is defined as 1 minus the purity of the choice state. And as I said, the figure merit here change a little bit. For example, if I have a channel which is unitary, as expect, we have entropy goes 0, so we don't have a good upper bound, for example. But if our map destroy information, that is the most radical scenario here, completely depolarizing, we have higher entropy, so this bound will be very tight. Okay, proving that we have this generalized canonical typicality. Just an example, we can, textbook example, we start with spins half in an external magnetic field, and we can decide if our canonical state is given by the usual canonical state, so our system is made of K system, or some kind of generalized subsystem which is our blurry detection here. And we see that the canonical distribution will be different, as expected. Same microcanonical state, different canonical distributions. And looking at our bound, and now to our generalized subsystem, we see that this kind of result is very robust. We don't need to thermodynamical limit. Only with n equal 8, we already have a very tight bound. In blue here, the solid, the field here are the right side of the inequality, and the open here is our bound. And you see as these here are, in order to fix the energy, we fix the quantity of impurities, quantity of excitation. So I fix the energy here. And for energies where we have many microstates, we have a very tight upper bound. So just finish. So conclusions here. Now, we present this framework, a generalized subsystem, in a statistical mechanics scenario to describe more general diffuse portions of a global system using quantum channels. So we generalize the notion of subsystem, generalize the canonical state. Here we demonstrate the canonical typicality are very robust. Demonstrate that canonical typicality remain robust even when subsystems are defined via quantum channels, and its connection to the entropy of a channel. Future directions, at least my perspective, is explore further application of generalized subsystem, maybe define heat, work, or how can we define such thermodynamical properties in this scenario, and maybe investigate more experimental context where we can effectively describe these generalized subsystems. So that's it. Thank you.
Thank you, Pedro. Questions?
Yeah, about the last point about applications. Probably you already know one of the standard applications of canonical typicality when you deal with closed systems is because they allow, for example, when you want to do numerics, you can, for example, suppose that you want to compute a trace instead of computing a trace that is very challenging. You simply pick a random state, you compute the quantity that you want on that state, and then you argue via typicality that the trace is essentially the same thing. I was wondering if this extension to quantum channels can have some application in the numerics for problems that are important in quantum channels that I don't know about. But I was wondering if you have some ideas on that.
No, I think I have less idea than you. I think.
I see. Okay.
But that's important because the quantum channel formula is a universe, right? Many applications, many areas. Here we focus on statistical mechanics, but we think that you can look at this typicality on. But of course, these channels must be, as we saw, we think the high entropy quantum channel.
So thanks for the talk. I find really puzzling still this thing of typicality because it seems that you do not require anything from the Hamiltonian of the composite system. On the other hand, if you think about eigenstate thermalization hypothesis, there you do require some features of your Hamiltonian, right? So is it possible to reconcile these two things? And
I think it's a good idea because in foundation of statistical mechanics, you have many degrees of the problem. Right? Equilibration and thermalization are different things, and also when you set an equilibration and this typicality scenario, it's not obvious how to reconcile the foundations of thermodynamics, really thermodynamics, with the foundation of our information thermodynamics. I don't know, but that's a good point.
Can I add a small comment about this because it's a point that is always confusing. Let's say typicality, what it's telling you is that if you pick a random state with very high chance, you will get a typical state, so a state that is structureless, let's say. ETH is much more than that. It's telling you that an Hamiltonian has its own eigenstates that are typical. So that is the crucial difference. ETH is a statement about the Hamiltonian and its eigenstate. Typicality is a statement about an Hilbert space. That is the main difference between the two.
It's not only about that also, because I mean, here typicality is just showing you that a random state is close to the average state, which is not necessarily the Gibbs state. If you assume that the Hamiltonian, you have a Hamiltonian with weak coupling, and the restriction you're doing is an energy shell, then typicality get you back the Gibbs state. But it's more general because the average state doesn't have to be the thermal state. So also that's the difference.
Okay, more questions? Okay, if not, we thank again, Pedro. And let me thank for all of the speakers of the day. Just a short announcement. Remember that tomorrow we will have in the afternoon the poster session. There will be a small cocktail as well. And right before the session, we'll make a group photo of the workshop as well. Okay. So given that, I see you guys tomorrow.